Dubai makes chocolate like nowhere else on earth. Inside its hidden factories, liquid cocoa meets gold standard precision as machines sculpt bars smoother than marble and richer than midnight. In this video, we step inside the secret world of Dubai's chocolate production to see how rare beans, high-tech tempering, and desert craftsmanship combine to create one of the most luxurious sweets ever made. The process begins with the reception of raw cacao beans. These arrive in large burlap sacks, which are automatically tipped into a stainless steel hopper. The hopper feeds a vibratory conveyor, shaking the beans in a controlled rhythm to remove debris and small stones. As the beans travel, high-powered magnets and air jets eliminate metallic fragments and lighter contaminants. Once cleaned, the beans move into the roasting chamber. This is a horizontal, drum-style roaster with precise temperature zones along its length. The beans are roasted between 120 degrees Celsius and 150 degrees Celsius for 30 to 45 minutes, depending on origin and moisture content. Inside the rotating drum, baffles lift and drop the beans repeatedly to ensure even exposure to heat. The surface crackles as volatile acids are driven off, and the aroma intensifies. Roasting profiles are strictly controlled using infrared sensors and thermal probes. After roasting, the beans exit into a rapid cooling system, a double-jacketed air cooling tunnel that quickly brings the temperature down to prevent over-roasting. As the beans cool, they're conveyed to the winnowing station. Here, a precision cracking roller gently fractures the outer shells. The mixture then passes through an ascending air column. Shells, being lighter, are blown upward and extracted into a cyclone separator. The heavier nibs fall downward, separated cleanly. The nibs are then routed into the liquor grinding system. This involves a two-stage reduction process. First, a coarse grinder reduces the nibs into a paste-like mass using granite rollers. This mass, still gritty, feeds into a 5-roll refiner. The rolls are made from hardened steel and arranged in descending gap widths. The rollers spin at increasing speeds to shear the particles down to 20 microns. During this stage, the paste becomes smooth and glossy, now known as chocolate liquor. From the refiner, the liquor is pumped into a conching machine. This is a long, horizontal tank with heavy granite paddles. The paddles rotate slowly but forcefully, kneading the liquor for up to 72 hours. During this process, frictional heat raises the temperature to 50-60 degrees Celsius. This drives off unwanted volatiles and enhances texture. As it churns, the chocolate undergoes subtle flavor transformation and becomes fluid, velvety, and aerated. At this stage, additional ingredients are introduced through precision feeders. Sugar is added via a sealed screw conveyor that meters crystalline particles in carefully measured doses. Milk powder, if producing milk chocolate, is pre-blended with a small portion of cocoa butter before being added. The mix is tested repeatedly with inline viscometers and particle size analyzers to ensure consistency. Next, the chocolate moves into the tempering system. This consists of 3 stainless steel heat exchangers that rapidly cycle the chocolate through defined temperature curves. The liquid chocolate is cooled from 45 degrees Celsius down to around 27 degrees Celsius and then reheated to 31 or 32 degrees Celsius. This carefully controlled crystallization process encourages the formation of stable cocoa butter crystals, Form 5, which gives the final chocolate a glossy finish and crisp snap. Once tempered, the chocolate is ready for molding. It flows into automated depositor heads mounted above polycarbonate molds. Each head features multiple precision nozzles controlled by servo motors. The nozzles deposit exact volumes of chocolate into the cavities, synchronized with the moving mold belt below. Vibration tables mounted beneath the molds shake rapidly, eliminating trapped air and evening out the surface. The molds enter a cooling tunnel, a refrigerated corridor where temperature and humidity are tightly regulated. Inside, a chilled airflow passes over the molds for 10 to 15 minutes, bringing the chocolate down to 8-10 degrees Celsius. This solidifies the product and locks in the tempered structure. Once cooled, the molds are inverted and gently flexed by mechanical arms to release the solid chocolates. They drop onto a food-grade conveyor belt, which directs them to the decorating and enrobing section. Here, high-speed cameras inspect the chocolates for surface defects, rejecting any that are misformed or marred. If filled or layered chocolates are being produced, the process diverges earlier. In that variation, the molds receive only a thin chocolate shell in the first deposit. These shells are then cooled, filled with praline, ganache, or fruit paste through precision piston fillers, and then sealed with a final layer of tempered chocolate before full cooling. Back on the main line, the finished solid chocolates enter the enrobing tunnel if they require coatings. This consists of a continuously flowing curtain of tempered chocolate falling from a weir system. The chocolates pass beneath the curtain on a wire mesh belt, receiving a uniform coating. Excess chocolate is blown off the bottom by air knives positioned beneath the belt. After enrobing, the products move through another cooling tunnel. This secondary tunnel is slightly longer and maintains cooler airflow at 6-8 degrees Celsius to ensure the coating sets with a uniform sheen. Inside, multiple temperature zones gradually reduce the product temperature to avoid bloom or condensation. Next is the decorating phase. This station uses robotic arms fitted with ultra-fine nozzles and stampers. The arms are guided by a 3D vision system to identify the orientation of each piece. Depending on the product, they may apply fine chocolate stripes, edible gold dust, cocoa powder, or even embossed logos using heat press stamping heads. Some lines include a nut topping mechanism that drops single pistachios or almonds onto the still soft chocolate surface with pneumatic precision. From here, the chocolates move to the buffering conveyor. This is a serpentine belt that temporarily holds products in case downstream machines slow down or halt. It prevents product collisions and maintains production flow without pause. Once flow resumes, the chocolates proceed to the wrapping line. The wrapping process begins with a high-speed feeder system. Chocolates arrive in single file along a narrow conveyor aligned by adjustable guide rails. As they approach the wrapping unit, an optical sensor scans each piece to verify orientation and spacing. A star wheel indexing system captures each chocolate in a rotating pocket, ensuring it enters the wrapping machine at precisely timed intervals. For individually wrapped pieces, the wrapping style depends on the product type, either fold wrap, twist wrap, or flow wrap. Fold wrap is used for rectangular or square chocolates. A continuous roll of foil, ends, often metallized polypropylene or laminated aluminum, feeds into a cutting station. A servo-driven knife slices the foil into perfectly sized sheets. A vacuum picker transfers each sheet onto a wrapping plate where a chocolate rests. Pneumatic folders quickly tuck each edge of the foil around the chocolate with clean, creased folds. And heated plates press the final seam to ensure adhesion without adhesives. In twist wrapping, used for rounded or pillow-shaped pieces, the chocolates are dropped into film pockets on a rotating turret. As they spin, two heated jaws grip the ends of the film and twist them in opposite directions in a single, fluid motion. The result is a tight double twist at both ends with no glue, secured purely by friction and film memory. Flow wrapping is reserved for bars or longer chocolates. Chocolates move onto a horizontal flow wrapper in perfect rows. A forming box folds a continuous film web into a U-shape around the moving product stream. Longitudinal sealing wheels fuse the film along the bottom seam using heat and pressure. Rotary end sealers then crimp and cut between each chocolate in one continuous motion. The result? A tight, seamless pillow pack with serrated edges. Once wrapped, products pass under a metal detector integrated with an automatic reject arm. Any contamination triggers an immediate air jet that diverts the product off the main line without interrupting flow. Approved chocolates continue to the labeling and grouping section. For chocolates requiring labels or tamper-evident seals, a label applicator aligns pressure-sensitive labels onto the wrapper surface with micron-level accuracy. For sealed tags or holograms, a rotary arm applies the label with static discharge to eliminate air pockets. High-speed vision systems verify placement and orientation, rejecting any misaligned units. Next, the wrapped chocolates are grouped into sets for final boxing. This is handled by a Delta robot pick-and-place system. Using 3 arms mounted on a gantry and guided by overhead cameras, the robots lift chocolates from the conveyor and deposit them into plastic or cardboard trays. The trays are held on index pallets that move step by step beneath the robot's reach. Depending on the SKU, arrangements may be linear rows, nested pyramids, or offset diagonals. If the product is a boxed chocolate assortment, the process diverges again. Assorted trays begin with an injection molded plastic insert, which is automatically placed into a folding carton. Chocolates are sorted by type and delivered to multi-head pickers. Each picker arm uses vacuum suction or soft rubber grippers to lift specific chocolates and place them in precise tray compartments. The sequence is synchronized to ensure correct assortment patterns. No duplicates, no gaps. Once loaded, these trays move to the lid application station. A folding carton blank is fed into a forming mandrel where pneumatic fingers erect and glue the box around the insert. A transparent film or foil seal is sometimes heat applied across the top, shrinking snugly into place. Then, a decorative lid is pressed on with a spring-loaded arm to achieve a flush seal. If a rigid luxury box is used, an entirely separate line assembles it. Die-cut cardboard is laminated with printed paper and hot-pressed into box forms. Magnets or ribbon closures are inserted automatically by articulated tools. The finished boxes are then transferred via robotic arm to receive their filled trays. From here, final boxing and case packing begins. Chocolates, now individually wrapped or boxed, arrive on a wide accumulation belt. Automatic collators organize them into bundles of 6, 12, or more, depending on shipping unit configuration. These bundles are pushed into carton erectors where flat corrugated blanks are folded around them, glued and pressed shut. Some lines use wraparound case packers. In this method, the grouped products are held stationary as a blank corrugated sheet is wrapped around all sides. Mechanical arms fold the flaps, apply hot melt glue, and compress the bundle into a sealed shipping case. These cases exit onto a short conveyor where industrial inkjet printers mark each side with batch numbers, timestamps, and QR trace codes. The case is then moved to the palletizing zone. Here, a robotic arm with a vacuum plate or gripper head arranges cases onto pallets. Each layer follows a programmed stacking pattern, alternating orientations for stability. After each layer, a slip sheet may be inserted by an automated feeder. Once the full stack is complete, often up to 2 meters high, the pallet is conveyed to a stretch wrapping machine. The stretch wrapper features a rotating turntable and a film carriage that moves vertically. As the table spins, the carriage stretches and applies multiple layers of plastic film under tension. This secures the load tightly and protects against moisture and dust. Some systems include a top sheet applicator that lays a waterproof plastic sheet across the top before wrapping. Finally, the fully wrapped pallets are conveyed through a weight check station and scanned by a vision system for final verification. They are now ready for shipment. A precisely manufactured, delicately handled series of chocolates transformed through over 24 distinct mechanical stages from raw bean to boxed luxury. For filled and layered chocolates, the factory employs a specialized multi-stage molding line. This system operates on a closed-loop conveyor that continuously cycles polycarbonate molds through a sequence of precisely timed stations. Each mold contains multiple cavities, and every station in the circuit performs a distinct action in the assembly of complex, filled products. The process begins with the shell forming station. A depositor head releases a measured volume of tempered chocolate into each mold cavity. Immediately, the molds move to a tilting station, where they are flipped and vibrated simultaneously. Centrifugal force causes the chocolate to coat the sides and bottom of each cavity evenly, leaving a hollow center. Any excess chocolate flows out and is reclaimed. After inversion, the molds pass under a chilled airflow, rapidly setting the shell. Once the shell is solidified, the molds continue to the filling station. This unit features servo-controlled piston depositors mounted above each cavity. The fillings are stored in heated hoppers to maintain fluid consistency. These can include hazelnut praline, fruit compotes, flavored ganache, caramel, or nut pastes, each delivered through dedicated nozzles. The depositors lower and inject precise quantities into each chocolate shell without disturbing the walls. Viscosity is controlled via inline heating coils wrapped around the filler lines. Every filling passes through mass flow meters to ensure consistency across thousands of units. Between each product type, CIP, clean-in-place systems, purge the lines with high-pressure heated water, followed by compressed air to eliminate cross-contamination. Next, the filled molds pass through a brief cooling tunnel. This lowers the filling temperature just enough to create a thin surface skin, ensuring it doesn't mix with the final chocolate seal. At the cap sealing station, another depositor head applies a top layer of tempered chocolate, sealing each cavity shut. This chocolate is deposited with high precision, covering the filling completely and fusing to the shell edges. Vibration tables beneath the molds remove trapped air and ensure a flush finish. The molds then enter a long cooling tunnel, typically spanning over 10 meters. This tunnel contains multiple chilled zones that gradually reduce product temperature from 30 degrees Celsius to under 10 degrees Celsius. The slow, staged cooling prevents shrinkage or cracking and allows the chocolate to fully contract away from the mold walls. Once cooled, the chocolates are ejected mechanically. Pneumatic plungers behind each mold cavity gently push the finished pieces downward onto a soft conveyor. These filled chocolates proceed to surface treatment. For layered chocolates, a similar system is used with key variations. After the first shell is deposited and cooled, a layer of inclusions, such as crushed nuts, cookie pieces, or fruit granules, is sprinkled into the mold by an oscillating vibratory feeder. A light pressure roller presses the inclusions into place. Then, a layer of filling is added, followed by a capping layer of chocolate. This creates a tri-layered cross-section when cut or bitten. Aerated chocolates follow a different method entirely. Here, the chocolate is first fed into a pressurized vacuum chamber. Under controlled vacuum, nitrogen gas is injected into the chocolate stream through a sparger, a perforated titanium rod. The gas forms microbubbles, which are then locked in by suddenly returning the chamber to atmospheric pressure. The now aerated chocolate has a mousse-like texture, yet remains stable once cooled. This aerated mixture is deposited into molds using modified volumetric heads that prevent bubble collapse. Because of the internal gas structure, aerated chocolates are cooled more gently to avoid rapid contraction. They pass through a specialized tunnel with fine-tuned temperature gradients that stabilize the internal structure. Some advanced variations include dual flavor split molds. These use two separate depositors operating in tandem, each filling half of the mold cavity with a different chocolate, such as milk and white or dark and ruby. A precision divider plate inside the nozzle ensures a clean, vertical split. The chocolates are deposited simultaneously, then vibrated and cooled, just like single origin types. Another variant involves inclusions in the chocolate itself. Before deposition, the base chocolate is mixed with particulate ingredients in a jacketed mixing bowl. These include puffed rice, freeze-dried fruit bits, chopped nuts, or biscuit crumbs. Agitators inside the bowl maintain even suspension. A positive displacement pump pushes the mixture through a large bore pipe to prevent clogging. Depositor heads with wider nozzles are used to handle the textured mass. For decorative layering, some lines use transfer film technology. A thin acetate film, printed with edible cocoa butter designs, is cut into sheets and placed on the bottom of each mold before chocolate is deposited. When the chocolate sets, the design transfers from the film onto the chocolate surface, creating intricate visual patterns. After cooling, the film is peeled away, leaving behind a vivid imprint. In other cases, chocolate pieces are stamped with embossed patterns or logos. After demolding, the chocolates move under a stamping head fitted with a heated metal die. The die is pressed lightly onto each piece, embossing it with a brand mark, pattern, or crest. The metal stamp is kept at 32 degrees Celsius, just warm enough to soften the surface without damaging structure. At this point, finished chocolates, whether filled, layered, aerated, or decorated, are directed toward the enrobing and topping station, if required. Some filled pieces receive an extra chocolate shell by passing through the enrobing curtain. Toppings such as sea salt flakes, crushed pistachios, or cocoa nibs are dispensed through multi-channel feeders synchronized with the belt speed. Each topping module includes a vibration sieve that controls granule size and drop rate. Sensors monitor belt occupancy to ensure no topping lands between products, minimizing waste. A gentle pressing roller may follow to embed toppings into the soft coating before cooling. Some premium chocolates are dusted with edible luster dusts or shimmer coatings. These powders are dispensed in an ultra-fine mist using electrostatic sprayers. The particles are positively charged as they exit the nozzle, adhering uniformly to the negatively charged chocolate surfaces. This creates a metallic or pearlescent finish with minimal overspray. For chocolates that require a hard shell glaze, a final step involves a rotating drum polisher. Chocolates are fed into the drum, which tumbles them gently while applying a thin mist of food-grade shellac or gum arabic. Internal warm air jets dry the glaze instantly, leaving a glossy, protective surface. Before reaching packaging, all finished chocolates pass through a multi-stage inspection tunnel. This includes laser-based shape detection, surface color analysis, and infrared temperature scanning. Products outside tolerance limits are ejected into designated bins. The final stage begins at the primary packaging line, where individual chocolates are grouped, positioned, and inserted into final, retail-ready formats. This step varies depending on the packaging style: rigid boxes, folding cartons, sleeve wraps, trays, tins, or multi-compartment assortments. Each format requires a dedicated configuration of pick-and-place systems, folder gluers, and sealing units. For rigid box assortments, chocolates arrive on an indexed belt and are picked by high-speed Delta robots equipped with vacuum suction heads. These robots place the chocolates into thermoformed plastic inserts, which are held stationary within open-bottomed rigid boxes. The inserts have precisely molded cavities matched to the contour of each chocolate piece. The robot arms adjust their speed and angle using dynamic feedback from overhead 3D scanners to avoid any misalignment. Once all cavities are filled, the boxes proceed to a film sealing station. Here, a roll of transparent BOP film is unwound, cut into sheets, and laid across the surface of the tray. A heated sealing plate presses the film into place, fusing it along the box edges to create a tamper-evident, airtight seal. The temperature of the sealing head is closely monitored by embedded thermocouples to maintain optimal adhesion without distorting the tray. For folding cartons, a different approach is used. Flat carton blanks, pre-printed and die-cut, are fed from a magazine stack into a carton erector. Mechanical arms fold the blank along pre-scored lines and apply hot melt glue in strategic points using precision nozzles. The forming mandrel compresses the carton into shape as it moves along the conveyor. Simultaneously, chocolates are grouped upstream by a collator belt, which aligns them into patterns matching the carton's internal layout. A pneumatic pusher slides each group into the open cartons as they move past. Once filled, the top flaps are folded and glued shut in a continuous motion. Some cartons are sealed with ultrasonic bonding, especially when glue-free closures are preferred. Specialty packaging formats, like sleeve-wrap trays, begin with a plastic or cardboard tray filled with chocolates using robotic placers. A printed sleeve, flat and folded, is then placed over the tray. A servo-controlled banding unit wraps the sleeve snugly and applies a heat pulse to seal the overlap. These sleeves often include die-cut windows or embossing, requiring precise alignment during application. For metal tins or embossed boxes, an overhead conveyor delivers empty tins into position beneath the filling heads. Chocolates are stacked by robotic arms, using multi-head grippers that rotate to fit varied geometries. Once filled, the tins are lidded by a lid placement mechanism equipped with pneumatic actuators. The lid is pressed into place with a calibrated force to ensure a snug fit without warping the metal structure. In premium lines, inserts and accessories are added next. These include product guides, tasting menus, or promotional leaflets. A sheet feeder places the inserts into each box before final closure. In some configurations, a robotic arm adds a protective paper layer or a foil cover between the chocolates and the lid. When ribbon closures are required, A secondary robot wraps and ties the ribbons automatically using twin spindle tensioners and soft grippers. After primary packaging, products move into the overwrapping unit, especially for premium and seasonal items. A continuous film roll feeds through a forming collar to enclose each box. A fin sealer applies pressure and heat along the bottom seam, while side sealers tuck and seal the ends into neat folds. A cooling plate downstream sets the film structure immediately after sealing. Optional tear strips or easy open tabs are applied at this stage. These are pre-cut film sections with embedded threads or adhesives that allow consumers to open the product without tools. A precision applicator adds them just before the film is sealed, embedding them into the plastic without disturbing box integrity. Next is batch labeling and coding. An inkjet printer or laser etcher marks each box with its batch number, manufacturing date, expiration date, and unique identifier. For export products, a vision verification system checks every printed code in real time and compares it against the product database. Any mismatch causes an automatic ejection by a pneumatic diverter. Then, boxes enter the case packing line. A robotic case packer arranges the boxed units into shipping cartons according to a pre-programmed pattern. Each case is assembled from flat blanks in an automatic erector. Once filled, the case is sealed using a high-speed tape applicator or hot melt glue system. The type of seal depends on the distribution channel and climate conditions expected during transit. Some boxes are stacked vertically, while others lie flat, depending on product fragility and presentation. If protective dunnage or air cushions are required, an integrated dispenser adds these into the case before sealing. Completed cases are printed with destination codes and passed through a check weigher, which confirms that each box is within expected weight tolerances. At the end of the line, full cases are transferred to the palletizing system. A robotic palletizer uses a vacuum plate or mechanical gripper to stack the cases onto pallets in a staggered pattern. The stacking sequence is designed for maximum load stability. Between layers, corrugated slip sheets are automatically inserted from a magazine. Once the pallet reaches the target height, typically 1.8 to 2 meters, it is conveyed to a stretch wrapping machine. The turntable rotates the pallet while a film carriage moves vertically, wrapping it in multiple layers of stretch film. Tension sensors ensure that the film applies consistent pressure without crushing the product. For export pallets, a top sheet dispenser adds a final moisture barrier before wrapping is completed. The final wrapped pallet moves to the finished goods staging area. Here, each pallet passes through a scanning tunnel that records its dimensions, weight, and barcode data into the warehouse management system. Automated guided vehicles, AGVs, retrieve the pallets and deliver them to temperature-controlled storage areas where ambient humidity and temperature are monitored continuously. In some specialized lines, climate conditioning is introduced post-packaging. Products enter a controlled chamber that simulates various storage conditions. For instance, rapid temperature cycling from 10 degrees Celsius to 30 degrees Celsius to ensure product stability. Chocolates are held in this chamber for several hours before release to shipping to verify that they maintain integrity under stress. Before release, a final quality sampling system selects random units from each production batch. These samples are conveyed to a physical and sensory testing station, where robotic arms manipulate the products through breakage resistance tests, surface gloss readings via reflectometers, and cross-sectional scanning via laser slicers. The internal structure is analyzed for air pockets, alignment of layers, and crystallization consistency. Hershey's chocolate production begins with the arrival of raw cocoa beans at its manufacturing plants, most notably in Hershey, Pennsylvania, where some of the largest scale chocolate operations in North America take place. These beans are imported from cocoa-producing regions around the equator, including West Africa and parts of Central and South America. Upon arrival, the beans are offloaded into receiving silos and moved into the first processing step: cleaning. Powerful vibrating screens, aspirators, and magnetic separators remove debris, stones, twigs, dust, and any metallic fragments that may have entered the shipment during transit. Following cleaning, the cocoa beans are fed into Hershey's proprietary roasting system. The roasting process is designed not just to sterilize the beans, but to precisely control flavor development. The machines are capable of adjusting roast temperature, humidity, and dwell time based on the origin, size, and moisture content of each batch. Beans are typically roasted at temperatures ranging from 120 to 160 degrees Celsius. This is where the characteristic chocolate aroma begins to develop, as volatile compounds are released and the Maillard reaction activates, producing hundreds of unique flavor notes that define Hershey's mild, sweet chocolate style. After roasting, the beans are cooled and moved to the winnowing section, where they are cracked open and the outer shells are separated from the valuable inner nibs. Winnowing is accomplished using a combination of mechanical cracking and airflow separation. The shells, now removed, are often collected and repurposed as agricultural mulch or biomass fuel. The nibs, the true essence of chocolate, contain both cocoa butter and cocoa solids and are now ready for the next phase, grinding. The nibs are fed into high-capacity industrial grinding mills, where intense mechanical shear forces break down the cellular structure and release the natural cocoa butter, forming a dense, fluid paste known as chocolate liquor. Despite its name, chocolate liquor contains no alcohol. This liquor is a pure, unsweetened, dark brown substance composed entirely of finely ground cocoa particles suspended in cocoa butter. From here, the liquor may go into temporary holding tanks or be immediately sent to blending tanks, depending on product demand. To make Hershey's classic milk chocolate, the chocolate liquor is blended with sugar, milk derivatives, cocoa butter, and small amounts of flavoring agents and emulsifiers. What makes Hershey's process unique is its use of fresh milk, originally pioneered by Milton Hershey himself, which is condensed and cooked on site. This milk is blended with sugar and chocolate liquor to form a slurry, which is then dried into what's known as milk crumb. The milk crumb is one of the keys to Hershey's signature, tangy, almost caramelized chocolate flavor. Unlike many European chocolate makers who use dry milk powders, Hershey's milk crumb production adds distinctive cooked dairy notes that have become synonymous with the brand's taste. The crumb mixture is then blended with additional chocolate liquor and cocoa butter in massive mixers to create a semi-fluid chocolate paste. This paste now contains all of the major components of Hershey's chocolate: milk solids, sugar, cocoa mass, and cocoa butter. However, it still needs to be refined to achieve the ultra-smooth texture that consumers expect. This refinement is achieved using a 5-roll mill, a piece of precision equipment where the chocolate paste is passed through a series of steel rollers that reduce particle size down to around 15 to 20 microns, small enough that the human tongue can no longer detect individual sugar or cocoa particles. Following refining, the chocolate mixture is fed into conchis, large horizontal vessels fitted with heavy-duty rotating arms. Conching is both a mechanical and thermal process in which chocolate is kneaded and aerated for several hours at controlled temperatures. During this stage, volatile acids are evaporated, off flavors are reduced, and cocoa solids become fully coated in cocoa butter, resulting in a more uniform flavor and mouthfeel. Hershey's conching times and temperatures are tightly guarded trade secrets, but generally range between 3 to 12 hours, depending on the chocolate type. Once conching is complete, emulsifiers like soy lecithin or PGPR may be added to improve flow characteristics and ensure the chocolate performs consistently during molding and enrobing. The now finished chocolate is transferred into tempering machines, where it is carefully cooled and reheated to stabilize the crystalline structure of the cocoa butter. Proper tempering is crucial to ensure the finished chocolate will have a glossy appearance, a sharp snap when broken, and resistance to fat bloom. Tempered chocolate is then routed to forming lines. For products like Hershey's milk chocolate bars or Hershey's Kisses, high-speed molding machines deposit the liquid chocolate into custom molds. These molds are vibrated to eliminate air bubbles and achieve uniform density before passing through long cooling tunnels. As the chocolate cools and solidifies, it contracts slightly and is released cleanly from the molds onto conveyors, ready for wrapping. Each chocolate piece is visually inspected, sometimes using high-speed cameras and vision systems, to ensure correct shape and fill. Hershey's Kisses, for example, go through dedicated foil wrapping machines that not only wrap each piece in branded foil, but also insert the iconic paper plume. Bars are fed into flow wrappers that apply sealed plastic or foil film, printed with lot numbers and expiration dates for traceability. From there, wrapped products are packed into cartons, sealed, labeled, and automatically palletized. Finished pallets are stored in climate-controlled warehouses maintained at stable temperatures and humidity to preserve texture, flavor, and appearance. Before any product is shipped out, samples from each production batch are tested in Hershey's quality control labs. There, technicians measure viscosity, particle size, pH, and fat content, and perform sensory evaluations to confirm that every batch meets the company's rigid standards for flavor and mouthfeel. Snickers, one of the most iconic candy bars in the world, is produced through a multi-stage industrial process that combines confectionery precision, mechanical engineering, and high-speed automation to create its distinctive layers of nougat, caramel, peanuts, and chocolate. Every bar must deliver the exact same ratio of texture and flavor, whether it's made in a facility in the United States, Europe, or Asia. With millions of bars produced daily, the manufacturing of Snickers is a tightly controlled operation with specific systems dedicated to each layer of the bar, all integrated into a seamless production line that ensures uniformity, food safety, and efficiency. From raw ingredient handling to final packaging, the Snickers factory operates with synchronized precision. Production begins with the preparation of the nougat layer, which forms the foundational base of every Snickers bar. The nougat used in Snickers is a whipped, chewy confection made from a combination of sugar, corn syrup, egg whites, milk powder, cocoa, and a small amount of salt. These ingredients are first loaded into industrial mixing vessels where they are cooked and then aerated. The sugar and corn syrup are heated together in a jacketed kettle until they reach a temperature between 115 degrees Celsius and 125 degrees Celsius. This heating process is tightly controlled through automated sensors that ensure consistent viscosity and prevent burning or crystallization. Once the syrup mixture reaches the desired temperature, it is transferred into a high-capacity continuous mixer, where egg whites and milk powder are added. Compressed air or nitrogen gas is also injected to whip the mixture into a soft, foamy texture. This aeration step is critical. It gives the nougat its characteristic lightness and chewiness. The temperature, gas pressure, and mixing speed are all precisely monitored by programmable logic controllers, which adjust the input in real time to maintain consistent product density and texture. The aerated nougat is then deposited as a thick slab onto a moving conveyor belt. This belt passes through a cooling tunnel that gradually reduces the temperature of the nougat slab to stabilize its structure. The cooling tunnel is divided into zones, each maintained at a different temperature to prevent rapid contraction, which could cause cracking or uneven density. Once cooled, the nougat slab is cut longitudinally into ribbons, the exact width of a Snickers bar, and then cross-cut into bar-sized sections using high-speed guillotine knives. These knives are synchronized with the conveyor's motion to ensure clean, accurate cuts without deforming the soft nougat. Next comes the caramel layer. The caramel used in Snickers is thick and elastic, designed to stretch but not melt under room temperature. It is made from a cooked blend of glucose syrup, sugar, milk solids, butterfat, and a carefully calibrated emulsifier. The cooking process begins in a steam-jacketed cooker, where the ingredients are brought up to approximately 118 degrees Celsius. The precise cooking temperature ensures the right balance between chewiness and flow. Overcooked caramel would become brittle, while undercooked caramel could seep through the nougat or ooze during packaging. Once cooked, the caramel is pumped into a depositor system that lays a continuous sheet of caramel over the cooled nougat ribbons. This depositor uses pressurized nozzles that spread the caramel evenly across the top surface of the nougat. The caramel is still warm and pliable at this point, allowing it to form a tight bond with the underlying layer. As the conveyor continues to move, the nougat and caramel combination enters another cooling tunnel where the caramel layer is firm to a stable consistency. Here again, the temperature gradient is critical. The cooling must be fast enough to stop flow, but slow enough to avoid separating from the nougat base. After the caramel is stabilized, whole roasted peanuts are applied. Snickers uses high-grade peanuts that are dry roasted on-site or sourced from dedicated peanut processors. These peanuts are first cleaned, sorted, and passed through color and size grading machines. Roasting is carried out in rotary drum roasters, where temperatures are maintained around 160 degrees Celsius. After roasting, peanuts are cooled rapidly using ambient or forced chilled air to stop the cooking process and retain crunch. The cooled peanuts are then sprinkled over the still sticky caramel layer using a controlled vibratory feeder. These feeders dispense peanuts in an even distribution, and excess nuts are collected and recirculated to avoid waste. Once applied, the peanut caramel nougat stack moves through a compression station where soft rollers press the peanuts gently into the caramel to ensure adhesion. This step is essential to prevent peanuts from falling off during enrobing and packaging. The multi-layer slab is then cut again, first lengthwise into individual bar width strips, then crosswise into single units. High-speed ultrasonic knives are often used in this phase to make clean cuts through the sticky peanut caramel mass without dragging or deforming the shape of the bar. These knives vibrate at ultrasonic frequencies, reducing friction and keeping each cut smooth and precise. As with earlier cutting stages, sensors track bar dimensions, and any piece that falls outside specified tolerances is rejected automatically. Now, the cut bars are conveyed into the enrobing chamber, where they are coated with milk chocolate. The chocolate used in Snickers is a proprietary milk chocolate blend containing cocoa solids, cocoa butter, sugar, milk powder, and emulsifiers. This chocolate is kept in tempering tanks where it is heated and cooled in a controlled cycle to form stable cocoa butter crystals. Proper tempering is crucial for ensuring that the chocolate coating is glossy, has the right snap, and doesn't develop fat bloom over time. Inside the enrober, each bar passes over a fine mesh conveyor that dips the underside of the bar in chocolate. A curtain of tempered chocolate then flows over the top of each bar, fully enrobing it. Excess chocolate is removed by controlled air jets or vibrating mechanisms, which ensure a consistent coating thickness without pooling or streaking. As the chocolate sets, decorative ribbons or textures may be applied to the top surface using nozzles or air patterns. After enrobing, the bars enter the final cooling tunnel. This tunnel is typically 20 to 30 meters long and divided into multiple zones, with temperatures gradually decreasing from around 15 degrees Celsius to 5 degrees Celsius. The goal here is to allow the chocolate to crystallize into a firm, uniform shell without cracks or surface defects. Conveyor speed and cooling tunnel temperature are constantly adjusted to account for changes in factory humidity or chocolate flow rate. Once the bars exit the cooling tunnel, they move to the packaging area. Here, vision systems inspect the bars for defects, such as incomplete coating, misshapen forms, or incorrect size, and reject any units that don't meet quality standards. Accepted bars move into a high-speed flow wrapping machine. This machine dispenses printed plastic film from large rolls, forms it into a sleeve around each bar, seals the ends and back, and prints lot numbers, expiration dates, and traceability codes onto the packaging. Bars are grouped and packed into cartons automatically, then palletized using robotic arms or automatic stackers. Each pallet is labeled with its production date, factory ID, and batch number, and stored in a temperature-controlled warehouse. Finished Snickers bars are shipped daily to retailers, wholesalers, and export hubs with real-time tracking through the company's logistics and ERP systems. This ensures traceability from raw ingredient to retail shelf and allows for rapid recall or investigation if any quality issue arises in the field. Snickers production is supported by continuous quality assurance throughout every phase. From incoming raw ingredients to the final product, quality technicians perform random sampling and laboratory testing for moisture content, peanut roast quality, chocolate temper index, caramel viscosity, and microbial counts. Every component, nougat, caramel, chocolate, peanuts, is monitored to within narrow tolerances. If even a single component batch shows deviation, it can be traced, flagged, and excluded from the production cycle. In addition to quality, food safety and hygiene are rigorously maintained. All machinery is subject to clean-in-place protocols, and workers adhere to strict sanitation and allergen handling rules. Due to the presence of peanuts, dedicated production zones and air handling systems are used to prevent cross-contamination with other product lines in multi-product factories. The Snickers production process is also increasingly supported by digital technology. Smart sensors, machine learning models, and real-time analytics are used to monitor equipment performance, detect subtle variances, and suggest preventative maintenance. Digital twins of the production line can simulate different production scenarios, like ingredient substitutions or temperature fluctuations, to predict impacts before they occur in the real world. This data-driven approach allows Mars, Inc., the manufacturer of Snickers, to continuously refine and optimize its production across multiple global sites. Twix is a beloved chocolate bar recognized globally for its iconic combination of crisp biscuit, chewy caramel, and smooth milk chocolate. Its appeal lies in the precise layering and the uniformity with which each bar delivers the same balance of texture and flavor. Behind its simple appearance is a highly engineered manufacturing process that seamlessly integrates baking, confectionery science, and automated packaging on a vast industrial scale. Producing millions of Twix bars daily in factories around the world requires meticulous coordination across every step of production, from dough mixing to chocolate enrobing, all operating under strict food safety protocols and quality control systems. The following in-depth look walks through the entire process, detailing how Twix is made in a modern factory environment, step by step, with over 1,600 words devoted to the subject. The process begins with the foundation of the Twix bar, the biscuit base. This shortbread-like component is central to the signature texture of Twix, light, crunchy, and buttery without being too sweet. The ingredients for the biscuit base include wheat flour, vegetable oil or shortening, sugar, salt, and leavening agents. These raw materials are delivered to the facility in bulk, typically stored in stainless steel silos or sealed containers to protect against moisture and contamination. The dry ingredients are conveyed into high-capacity horizontal mixers, where they are combined with fats and a small amount of water. These mixers are programmed to replicate the specific time, temperature, and mixing intensity needed to create the ideal dough consistency. Overmixing is carefully avoided to prevent gluten development, which would make the biscuit tough rather than tender and crisp. The dough is monitored for temperature, moisture content, and texture using inline sensors, ensuring consistency across every batch. Once mixed, the dough is transferred to a sheeting machine. This equipment rolls the dough into a uniform sheet of precise thickness, typically between 5 to 7 millimeters, depending on the specific product variant. The sheet passes through multiple sets of rollers to ensure evenness, then moves toward a rotary cutter that stamps out the biscuit fingers. Each finger is carefully spaced on a baking band to prevent sticking or deformation during baking. Excess dough, or webbing, is collected automatically, recycled, and fed back into the mixer for reuse, minimizing waste. The cut biscuits are conveyed into a tunnel oven, often more than 30 meters long, and divided into multiple temperature zones. The ovens are typically gas-fired and utilize forced convection to ensure even heat distribution. Baking profiles are carefully managed. The temperature starts lower to allow for expansion and rises toward the middle and end of the tunnel to set structure and achieve the golden brown exterior. The baking process typically lasts around 8 to 12 minutes. The final product emerges dry, crisp, and structurally sound to support the next layers of caramel and chocolate. After baking, the biscuits are cooled on a long spiral or tiered cooling conveyor. It is essential that they reach ambient temperature before caramel application, as residual heat could soften the caramel or cause bonding inconsistencies. Airflow systems within the cooling unit are calibrated to prevent moisture buildup, which could compromise the crispness of the biscuit layer. Next is the caramel layer, one of the most technically challenging aspects of the Twix manufacturing process. The caramel must be viscous enough to form a thick, even layer on the biscuit, yet firm enough to retain its shape during cutting, enrobing, and packaging. It must also stretch slightly when bitten into, without melting or breaking apart. The caramel is prepared in large, jacketed cooking kettles or continuous caramel cookers. The ingredients, glucose syrup, sugar, milk solids, fats, and sometimes salt and flavorings, are heated to a controlled temperature around 118 to 120 degrees Celsius. Cooking caramel to the correct temperature is critical. Any deviation can result in too hard or too runny caramel. The factory's automated control systems monitor brix levels, temperature curves, and viscosity in real time. Adjustments are made instantly if readings deviate from the set parameters. Once cooked, the caramel is pumped into a depositor system. This system deposits a continuous ribbon of hot caramel directly onto the cooled biscuit fingers, which are now moving along a precision conveyor belt. Depositors can be adjusted to control caramel height and width, ensuring even coverage. The caramel must adhere firmly to the biscuit and cool rapidly to a semi-firm consistency to hold its shape through the subsequent chocolate enrobing process. The bars now enter a cooling tunnel for caramel setup. This tunnel is maintained at a lower ambient temperature and spans several meters to allow gradual cooling without thermal shock. As the caramel cools, it solidifies just enough to support chocolate coating without running or shifting. This balance is critical for appearance, structural integrity, and mouthfeel. Once the biscuit and caramel layers are firmly bonded, the bars proceed to the chocolate enrobing phase. This is where each Twix bar is fully coated in a layer of milk chocolate. The chocolate used is a proprietary blend formulated specifically for Mars, Inc., and it includes cocoa butter, milk powder, cocoa solids, sugar, and emulsifiers, such as soy lecithin, to ensure proper flow. The chocolate is first tempered, a process that involves heating, cooling, and reheating to encourage the formation of stable cocoa butter crystals. Proper tempering gives the final chocolate coating its shine, snap, and resistance to fat bloom. In large-scale operations, tempering is achieved using continuous tempering machines that monitor crystal formation, viscosity, and flow rate. The tempered chocolate is pumped into an enrober, which is essentially a tunnel where a curtain of chocolate flows from above and a shallow pool coats the bottom. The bars pass through this curtain and are submerged briefly in the bottom coating layer, ensuring all sides are covered. Air knives or vibrating plates remove excess chocolate, and decorative features, such as surface ripples, may be added by adjustable nozzle heads or vibration patterns. The chocolate-coated bars are immediately conveyed into another cooling tunnel, this one much longer and colder, designed to gradually bring the chocolate to a solid state without creating bloom or surface imperfections. The cooling tunnel maintains a strict temperature gradient, starting around 18 degrees Celsius and lowering to 10 degrees Celsius by the end, over a 5 to 10 minute period. As the bars exit the cooling tunnel, they are fully formed Twix bars, but they're not yet individually packaged. They move directly into the high-speed wrapping area. Each bar is aligned and spaced using puck systems or lane guides to ensure it enters the flow wrapping machine correctly. Here, rolls of branded film are fed into the wrapper, folded tightly around the bar, and sealed on all sides using heat and pressure. The film is pre-printed with logos, batch codes, nutritional data, and sometimes promotional graphics. Each wrapped bar is weighed and passed through metal detectors or X-ray scanners to ensure it meets food safety standards. Any bar outside of weight tolerance or showing contamination is automatically diverted. Accepted bars are grouped into multi-packs or display boxes using robotic pickers or diverters, then loaded into shipping cartons. The cartons are coded with tracking data and palletized using automatic palletizers. Each pallet is scanned into inventory and staged for shipping. Throughout the factory, quality control technicians pull samples at regular intervals to test for key performance attributes: biscuit density, caramel thickness, chocolate adhesion, weight, sensory characteristics, and packaging integrity. The factory also operates under a HACCP framework, meaning each step of the process is mapped for potential hazards and monitored with critical control points. Twix manufacturing is highly dependent on repeatability, and thus, much of the factory's infrastructure is built around statistical process control and automation. PLCs communicate with sensors on every machine, feeding data to a centralized control room. This enables supervisors to watch live readouts of oven temperatures, caramel cooker output, chocolate temper readings, fill weights, and wrapper speed, all updated every second. Alarms and automatic corrections are built into the system, allowing for real-time adjustments without stopping production. Beyond process precision, Twix production lines are designed for flexibility. Factories can run product variations including Twix miniatures, Twix ice cream bars, Twix cookies and cream, or seasonal additions like white chocolate or dark chocolate. Changeovers between product formats involve switching molds, adjusting depositor nozzles, changing film rolls, and flushing chocolate lines, all of which are guided by detailed standard operating procedures to avoid cross-contamination and ensure food safety. Once finished, Twix bars are shipped to distribution centers or directly to retailers. During shipping, temperature control remains important, particularly in warm climates where chocolate is susceptible to melting. Pallets may be moved using temperature-controlled trucks or packed with insulation to protect product integrity. Inventory is rotated on a first-in, first-out basis to ensure freshness and shelf life management. At the retail end, Twix must retain not only its visual appeal, but its textural signature. The snap of the biscuit, the chew of the caramel, and the smoothness of the chocolate are all the result of hundreds of synchronized steps and checks across a production system built for consistency at scale. From ingredient sourcing to the final shipping pallet, every detail is fine-tuned to preserve the brand's identity and ensure that each bite of Twix tastes exactly as expected: crisp, creamy, and perfectly layered. The production of a Mars bar begins with the formulation and creation of its first major internal layer, the nougat. This nougat isn't the brittle kind you might find in traditional nut candies. Rather, it's a whipped, creamy, slightly chewy foundation that gives Mars bars their signature texture. Creating this nougat at industrial scale is a carefully engineered process that blends confectionery science with mass production machinery and strict environmental controls. Before the first batch of nougat is made, however, the ingredients themselves must be prepared and stored according to strict protocols. The base ingredients for the nougat are sugar, glucose syrup, water, fat typically palm or shea oil, dried milk powder, cocoa powder, and whipped egg white or egg albumin. All these materials arrive at the Mars manufacturing facility in bulk, delivered in tankers, tote bags, or sealed sacks. Each delivery is logged, barcoded, and entered into the site's inventory system. But before any ingredient enters production, it must pass Mars internal quality standards. All dry ingredients, such as sugar and milk powder, are transferred into enclosed silo systems using pneumatic conveyors. These silos are climate controlled and fitted with HEPA filtration to prevent contamination from dust or ambient air. Each ingredient batch is tagged with a barcode that traces it back to its supplier, production date, and previous storage conditions. For example, sugar may be tested for grain size, purity, and color using laser granulometry and ICUMSA color unit analysis. If it's outside tolerance, it's rejected immediately. Liquid ingredients like glucose syrup and oils are offloaded into jacketed stainless steel storage tanks through filtered, food-grade hoses. These tanks maintain the ingredients at set temperatures to ensure proper viscosity for pumping during production. Glucose syrup, for instance, is kept at around 40 degrees Celsius to remain fluid enough to move through piping without crystallizing. Oils are similarly heated and agitated to prevent separation or solidification. Once all components have been approved and staged, the first step in actual nougat production begins in a dedicated mixing chamber. This space is sealed off from other parts of the factory and maintained at specific humidity and temperature levels to preserve the quality and structure of the aerated product. Airborne particles are filtered through a multi-stage air filtration system, and stainless steel surfaces are sanitized before each production run. Nougat is made in large capacity continuous mixers, automated machines that blend ingredients while precisely managing flow rate, temperature, and mixing speed. In a traditional batch process, workers would mix sugar and glucose syrup with water and cook it to a specific temperature. But in Mars's high-speed factories, this process is carried out on a continuous flow basis, meaning raw ingredients are metered into the cooking system in real time, mixed, cooked, and then aerated in a constant stream. First, sugar, glucose syrup, and water are combined in a jacketed mixing vessel and brought up to temperature using indirect steam heating. The mixture must reach roughly 115 to 120 degrees Celsius, hot enough to dissolve all solids and achieve the correct consistency for whipping, but not so hot that caramelization occurs. Inline refractometers monitor the Brix level, sugar concentration, constantly, sending digital signals to a control system that adjusts syrup feed rate or cooking temperature as needed to stay within spec. Once the syrup reaches target temperature and concentration, it's transferred to a cooling chamber, where it's rapidly brought down to around 70 to 80 degrees Celsius using chilled water jackets. This temperature reduction is critical. It stabilizes the syrup mixture and prepares it for aeration with egg whites or albumin, which cannot be added while the base is too hot without denaturing the proteins. Now comes the aeration stage, where the characteristic lightness and chew of the nougat is created. A pre-prepared egg albumin solution is metered into the cooled sugar syrup in a continuous aerator. This machine functions much like a planetary mixer, but at vastly greater speed and scale. Blades spin at extremely high RPMs inside a sealed chamber, while air is injected under pressure. The result is a fluffy, stable foam that has the volume and consistency of whipped marshmallow. The air injected into the aerator is sterile and dry, supplied by an inline compressed air system equipped with microbial filters and dehumidifiers. Pressure, temperature, and air-to-liquid ratio are all controlled automatically via programmable logic controllers, PLCs, which adjust mixing speed and flow rate to maintain uniform aeration. If the density of the nougat mixture falls outside of target specifications, measured by inline densitometers, the system automatically corrects the air or syrup flow or alerts operators to intervene. At this point, cocoa powder and dried milk are added to the base. These ingredients give Mars Bar Nougat its unique color and rich malted taste. They are added using powder feeders that continuously meter the dry materials into the aerated mass as it exits the mixer. This blending occurs in a sealed paddle mixer with gentle, controlled agitation to avoid collapsing the foam structure. The resulting mixture is a warm, chocolatey nougat paste with a light, stable structure and a semi-elastic texture. Now that the nougat base is formed, it must be shaped and cooled. The nougat flows out of the mixer onto a stainless steel conveyor belt, forming a continuous slab about 2 to 3 centimeters thick. This slab passes through a chilling tunnel, where it is gradually cooled from around 60 degrees Celsius to just below ambient temperature. The tunnel uses recirculated cold air, zoned in multiple sections, to cool the nougat evenly without inducing condensation or hardening the outer surface too quickly. As the slab exits the chilling tunnel, it enters a cutting station. Rotary guillotine knives, synchronized with the belt speed, slice the slab crosswise into narrow ribbons, each of which will become the base layer of a Mars bar. These ribbons are then cut lengthwise by inline blades or ultrasonic cutters, creating rectangular nougat centers of uniform size. Every bar section is scanned by vision systems to check for dimensional consistency, length, width, and height, with auto-reject mechanisms removing any pieces that fall outside tolerance. The formed nougat segments are now ready to receive their second major component, the caramel layer. But before caramel is deposited, the nougat sections are spaced and aligned using lane diverters and product guides, ensuring that each bar proceeds uniformly through the next phase of production. The segments then pass into a buffer zone where their temperature is stabilized to prepare for caramel application. Now that the nougat segments are cooled, cut to precise dimensions, and cued in alignment on the conveyor system, the next phase in the Mars chocolate bar manufacturing process begins: the production and deposition of the caramel layer. This caramel is not a generic topping, it's one of the signature components that defines the textural and flavor contrast of a Mars bar. Creating this layer at scale requires a specialized process that integrates continuous cooking, emulsification, temperature control, and precision depositing, all engineered to work seamlessly within the speed and flow of a high-volume confectionery production line. The caramel used in Mars bars is made from a carefully balanced combination of sugar, glucose syrup, sweetened condensed milk or milk solids, and a specific blend of fats and emulsifiers. It's cooked to achieve a particular consistency, not too firm, not too runny, with a creamy chew that holds its shape during wrapping and storage, yet yields easily when bitten into. The production of caramel begins in a dedicated cooking area, separate from the nougat line, but synchronized with it to maintain constant throughput. All ingredients are stored in bulk near the cooking zone. Sugar and milk powders are gravity-fed from silos into high-shear premixes, while glucose syrup and fat are pumped in from temperature-controlled tanks. The emulsifiers, such as mono and diglycerides, are introduced through metering pumps in very small, tightly controlled amounts to help ensure smooth texture and fat water dispersion. A water phase may also be introduced at the start to aid in initial dissolution and prevent localized overheating. The entire mixture is first blended in a jacketed stainless steel preheating tank, where it's brought to a uniform temperature of around 70 to 80 degrees Celsius. This pre-cooking stage ensures that all ingredients are fully homogenized before entering the main caramel cooker. From here, the caramel mix is pumped continuously into a vacuum caramel cooker, a specialized machine that allows rapid, even heating while removing excess water to control the final solid's content and viscosity. Vacuum caramel cookers work by reducing the internal pressure in the cooking chamber so that water boils off at a lower temperature. This is crucial to avoid burning the sugars or overcooking the milk solids, which could lead to bitter notes or textural instability. Inside the cooker, the mix is heated to between 115 degrees Celsius and 120 degrees Celsius. The target is to achieve a final water content of around 6 to 8%, with a sugar concentration of roughly 80 to 85 brix. Inline refractometers monitor this constantly, and the cooker adjusts residence time or heating level as needed to meet the spec. Once cooked, the caramel exits the cooker as a thick, glossy liquid with a rich golden brown hue. But before it can be applied to the nougat, it must be slightly cooled and tempered to a very specific range, typically between 45 degrees Celsius and 55 degrees Celsius. This cooling step stabilizes the caramel structure, allowing it to flow evenly during deposition without dripping or bleeding into the nougat layer. Cooling is performed in a jacketed holding tank equipped with slow-speed agitators that prevent crusting and keep the mixture homogeneous. With the caramel at the correct temperature, it's piped toward the depositing station. Here, the aligned nougat segments are conveyed under a continuous curtain-style depositor or a series of timed nozzles. Each piece receives a uniform layer of caramel, typically around 5 to 6 millimeters thick, depending on the final product specification. The depositor is precisely synchronized with the line speed, often using servo motors and optical sensors, so that each caramel stream lands squarely on the nougat block without overflow or excess. In higher speed lines, a pre-formed caramel sheet may be used instead. In this method, caramel is spread onto a separate cooling belt, allowed to set into a thin slab, and then laminated onto the nougat in one continuous motion using compression rollers. This technique allows better layer thickness control at very high production speeds and ensures cleaner edges for slicing. Once the caramel is applied, the dual layer bar now enters another cooling tunnel, usually a multi-zone refrigerated belt system that brings the caramel from 50 degrees Celsius down to just under 20 degrees Celsius. This cooling step must be gradual and controlled. Too rapid, and the caramel may contract unevenly, leading to separation from the nougat. Too slow, and it may remain sticky, interfering with the next step. Chocolate enrobing. During cooling, the layered bar is gently compressed by a roller to ensure adhesion between nougat and caramel. Then, it's passed through edge trimmers, which shave off the sides of the slab to produce perfectly square bars with clean, vertical sides. These trimmed edges are not wasted. They are collected via vacuum conveyors and reprocessed, either remelted or reformed, depending on factory protocol. The bar, now comprised of a cooled nougat base and a bonded caramel layer, is next cut into individual pieces using high-speed guillotine cutters. These are precision machines equipped with hardened stainless steel blades or ultrasonic cutting systems that minimize drag and preserve edge integrity. Each piece is exactly the length and width of a finished Mars bar, around 10 centimeters long and weighing roughly 51 to 57 grams, depending on the market. As the bars are cut, they are spaced out evenly using puck conveyors or lane dividers, aligning them perfectly for entry into the chocolate enrobing section. The temperature, moisture, and dimensional uniformity of each bar are verified by inline sensors and vision systems. Bars that are cracked, too short, or unevenly shaped are automatically diverted off the line for manual inspection or rework. At this stage, we transition into the enrobing process, the iconic step where each bar is coated in a smooth layer of Mars' proprietary milk chocolate blend. This chocolate is stored in large tempering tanks, located just prior to the enrober. These tanks keep the chocolate at the ideal crystallization state, ensuring a glossy finish and firm snap after cooling. The chocolate used in Mars bars is a blend of cocoa liquor, cocoa butter, sugar, and milk solids, with added emulsifiers like soy lecithin to enhance flow properties. The tempered chocolate is pumped into the enrober, which is essentially a tunnel lined with a bottoming section to coat the base of each bar, and a curtain section to drape chocolate over the top and sides. Each Mars bar passes first over a shallow pool of chocolate to coat its underside, then directly beneath a flowing curtain that envelops the rest of the bar. A gentle stream of warm air is directed across the top to remove excess and create a rippled surface texture, a distinctive feature of the Mars bar. After enrobing, the bars are conveyed into the cooling tunnel, an extended refrigerated belt system approximately 20 to 30 meters in length. Inside, the environment is segmented into zones that gradually lower the temperature of the bars from around 32 degrees Celsius to 10 degrees Celsius. This staged cooling helps the cocoa butter in the chocolate crystallize properly, locking in the sheen and texture while avoiding fat bloom or streaks. Throughout this tunnel, air humidity is tightly controlled, generally under 50%, to prevent condensation on the chocolate. Dew point sensors and fans work in tandem with the refrigeration units to maintain a stable microclimate. The bars spend 5 to 8 minutes in this tunnel before emerging with fully set coatings, ready for packaging. As the cooled and finished bars exit the tunnel, they're fed into accumulation conveyors and grouped for wrapping. Each bar passes through a flow wrapping machine where printed film is unwound, formed into a sleeve, and sealed around the product. The wrapper is then crimp sealed on both ends and trimmed. These wrapping machines can process hundreds of bars per minute, and each wrapped bar is weighed and scanned before being discharged onto final packing belts. At this point, the product is visually indistinguishable from the Mars bar found on store shelves, but the process is still not finished. The next stage involves secondary packaging, grouping bars into boxes, cartons, and shipping trays, and preparing them for distribution. As the fully formed, enrobed, and cooled Mars bars make their way off the production line, they enter the final stages of the factory process, beginning with high-speed wrapping and continuing through automated boxing, palletization, storage, and outbound logistics. These downstream systems are critical not just for protection and presentation of the product, but also for ensuring traceability, quality retention, and supply chain synchronization. While the visible production, the mixing, cooking, cutting, and coating is complete, the final packaging and handling stages are no less intricate, built on robotics, data systems, and industrial automation designed to manage millions of units every day. The first stop is the wrapping station. Here, each Mars bar moves along the conveyor belt in single file toward the flow wrapping machine. This machine feeds a continuous roll of printed film into a series of folding arms and sealing jaws. As each bar enters, the film wraps around it in a tight, tubular sleeve, and heated crimp jaws at either end form the back seal and the end seals simultaneously. The temperature of these jaws is maintained within a few degrees of the sealing material's activation point to ensure strong, clean closures without melting or burning the film. Mars uses multi-layered packaging films that are designed not only to provide barrier protection against oxygen and moisture, but also to deliver the tactile feel and gloss that customers expect from premium chocolate packaging. The inner layer is typically a heat-sealable polymer. The middle layer may include aluminum or metallized PET for barrier properties, and the outer layer is printed with brand artwork and product information. The printed designs are registered with high-precision sensors, so every bar's logo aligns perfectly. Any misregistered wrapper is automatically detected and rejected by an optical scanner system. Once sealed, the wrapped bar passes over a check weigher, an in-motion scale that ensures the final packaged weight is within tolerance. If a bar is over or underweight, even by a gram, it's automatically diverted. Next, each unit is passed under a metal detector, which checks for any possible foreign objects that could have entered the bar during earlier processing stages. These systems are highly sensitive and calibrated daily with test pieces. Some plants also employ X-ray machines that detect not just metal, but dense, non-metallic contaminants, such as glass or stone. Bars that pass all inspections continue down the conveyor toward the cartoning line. Depending on the intended retail format, bars may be grouped into multi-packs, retail-ready trays, or shipping cartons. Robotic arms, or high-speed diverters, organize the flow of individual bars into stacks, 4, 6, 10, or 12 bars wide, and gently push them into pre-folded cardboard sleeves or boxes. These secondary packages are then sealed using hot melt glue or tuck-in flaps, depending on market requirements. Each package receives a printed label with batch number, timestamp, factory ID, and possibly a QR code for inventory tracking. From here, boxed products are routed to the palletizing station. Robotic palletizers pick up full cases using vacuum grippers or mechanical arms and stack them on wooden or plastic pallets in precise formations. Each layer is arranged to optimize space, balance, and load stability. Between layers, some systems add cardboard slips or corner protectors for reinforcement. Once the pallet reaches its programmed height, typically 1.6 to 1.8 meters, it's wrapped in stretch film by an automatic wrapper, which rotates the pallet while dispensing the film under tension to secure the load. The wrapped pallets are then fitted with pallet labels that include the SKU, total unit count, gross weight, destination code, and a unique identifier that ties back to the factory's internal tracking system. These labels are printed by thermal printers and verified by barcode scanners before the pallets are cleared to enter the finished goods warehouse. Before we go further, it's important to recognize the role of Mars factory control systems in managing this entire post-production phase. All equipment is integrated into a centralized manufacturing execution system, MES, that tracks every product in real time. Each bar, box, and pallet carries data, embedded in barcodes or RFID tags, about when it was made, on which line, using which ingredients, and under what conditions. This traceability is a cornerstone of food safety compliance and internal quality assurance. The finished goods warehouse is where the newly palletized bars await shipment. This warehouse is fully climate controlled to maintain optimal temperature and humidity for chocolate storage. Temperature is held at 18 to 20 degrees Celsius with relative humidity below 55% to prevent bloom, melting, or texture changes. Air circulation systems keep temperature consistent throughout the space, while insulation and vapor barriers prevent external fluctuations from impacting internal conditions. Inventory in the warehouse is managed using automated guided vehicles, AGVs, or forklifts equipped with real-time location systems. When pallets are stored, they're scanned into the warehouse management system and placed according to distribution priority. High turnover products are stored closer to the shipping bays, while seasonal or export variants may be stored deeper in the racking system. The storage time for any batch is typically less than a week, as Mars factories operate on just-in-time logistics, pushing product out daily to meet distributor orders. When shipments are requested, the warehouse team receives a digital pick list. AGVs or operators retrieve the designated pallets, verify them via handheld scanners, and stage them at the outbound docks. Before loading, each shipment is inspected to ensure it matches the order specification, is within temperature tolerance, and has intact pallet wrapping. Refrigerated or climate-controlled trucks are often used for long-distance shipments or deliveries to regions with high ambient temperatures. Loading is done using dock levelers and roller systems to ensure smooth movement and prevent tipping. During transit, temperature loggers accompany the shipments, recording data at set intervals. These loggers are checked upon delivery, and if any deviation from the acceptable range is detected, the shipment may be flagged for inspection or rejection. Mars also monitors customer feedback, market audits, and in-store quality surveys. Samples of each production lot are retained in climate-controlled storage at the factory for shelf life testing. These retained samples are periodically tested for appearance, taste, texture, and microbiological stability over the course of months, ensuring that every production protocol performs as expected long after the product has left the plant. Parallel to all of this is a dedicated quality control laboratory. Here, daily production samples are subjected to physical and chemical analysis. Moisture content, fat content, sugar crystallinity, pH, and emulsion stability are checked using instruments like Carl Fisher titrators, differential scanning calorimeters, and viscometers. Sensory panels trained in Mars' specific flavor and texture profiles evaluate samples for aroma, mouthfeel, and aftertaste. Auditors regularly conduct surprise inspections, testing product against regulatory standards in every region the factory exports to. Some facilities even run accelerated aging chambers, simulating 6 months of shelf life in a few weeks using controlled temperature and humidity cycling. This allows the company to predict how new packaging or ingredient changes may impact long-term stability before releasing them to the market. Within the final layers of Mars' chocolate bar manufacturing process lies an often unseen yet deeply critical infrastructure dedicated to innovation, iteration, and global standardization. While the production lines are optimized for high-speed consistency, behind the scenes, the company operates pilot plants and R&D laboratories, where new formulations, production methods, and equipment calibrations are continuously tested, refined, and validated before they're deployed across global facilities. Every Mars chocolate bar, regardless of where it is produced, in the United States, the United Kingdom, or other licensed manufacturing hubs, must adhere to an extremely narrow window of variation. This means the bars must look, taste, feel, and behave identically, despite being produced in plants thousands of kilometers apart. Achieving this demands extensive process documentation, real-time data comparison, and coordinated updates to recipes and equipment settings across all sites. Pilot plants, often located adjacent to main production facilities, house miniature versions of the full-scale equipment, scaled-down mixers, depositors, tempering tanks, and enrobers, used not just for prototyping new flavors or bar formats, but also for stress testing ingredient substitutions, adjusting for new cocoa sources, or modifying emulsifier levels in response to regional ingredient availability or regulation. A new Mars bar variant, such as one with an added layer of cookie or a salted caramel flavor, may go through dozens of test batches before scaling. Each trial is evaluated not just for consumer preference, but for how it performs on actual equipment. Does the caramel spread at the correct rate on moving belts? Does it maintain form through the cooling tunnel? Does the chocolate enrobe correctly without altering crystallization time? These questions are answered with data from test runs that are digitally logged and used to generate predictive models before any large-scale production begins. Digital twins, virtual simulations of real production environments, are increasingly being used in these trials. These tools model fluid dynamics, thermal behavior, and mechanical stress on ingredients during cooking, cooling, and transport. They allow engineers to simulate a dozen line changes without touching a single piece of physical equipment, drastically accelerating the pace of safe innovation. Once a new process is approved, Mars' global standardization team prepares comprehensive change packs, which include updated process parameters, safety protocols, ingredient specs, equipment calibration charts, and software updates. These packs are then distributed to all regional manufacturing hubs, often followed by remote training sessions or on-site visits to ensure implementation is seamless. This global coordination ensures that whether you open a Mars bar in Chicago, Sydney, or Madrid, the experience is identical, down to the snap of the chocolate, the elasticity of the caramel, and the melt rate of the nougat. The process begins with the sourcing of raw ingredients, including hazelnuts, sugar, cocoa powder, palm oil, skim milk powder, and vanillin. These ingredients are delivered to Nutella factories in massive quantities, requiring large-scale handling infrastructure. Hazelnuts, one of the key components of Nutella, are often sourced from Turkey and Italy, two of the largest hazelnut producers in the world. Upon arrival at the factory, hazelnuts are stored in enormous silos or temperature-controlled storage rooms to maintain their freshness. The silos are made of food-grade stainless steel and designed to protect the nuts from humidity and contamination, while allowing for precise dispensing into the production line. The first step in processing the hazelnuts is cleaning. Hazelnuts arrive in bulk shipments, often mixed with debris such as shells, stems, and dirt. To address this, the factory uses a series of cleaning systems that include vibrating screens, air classifiers, and magnetic separators. The vibrating screens shake the nuts to separate them from larger debris, while the air classifiers blow away lightweight impurities like husks and dust. Magnetic separators are also used to detect and remove any metallic particles that might have entered the shipment during harvesting or transport. Once cleaned, the hazelnuts undergo visual inspection using high-speed optical sorting machines equipped with cameras and sensors. These machines identify and remove any defective hazelnuts, such as those with discoloration, cracks, or signs of mold. After cleaning, the hazelnuts move to the roasting stage. Roasting is a crucial step in developing the rich, nutty flavor that characterizes Nutella. In the factory, this is achieved using massive industrial roasting ovens. These ovens are designed with rotating drums or conveyor belts to ensure even roasting. The temperature is carefully controlled, typically ranging between 280 and 320 degrees Fahrenheit, depending on the size and moisture content of the hazelnuts. Sensors monitor the temperature and time to ensure consistency, as over-roasting can lead to bitterness, while under-roasting can result in a lack of flavor. The entire roasting process is automated, and the equipment is designed for continuous operation to handle the high volume of hazelnuts required for production. Once roasted, the hazelnuts are transferred to grinding machines. These machines are equipped with heavy-duty stainless steel blades and rollers that crush the nuts into a fine paste. The grinding process occurs in multiple stages, with each stage further reducing the particle size of the hazelnut paste. In the initial stage, the nuts are coarsely ground into a chunky paste. In the subsequent stages, the paste is refined into a smooth consistency, with particle sizes measuring less than 30 microns. This ultra-fine grinding is essential for achieving Nutella's creamy texture. The equipment used in this process, such as colloid mills and ball mills, is highly specialized and designed to operate under high pressure and at precise speeds. The resulting hazelnut paste is collected in large stainless steel tanks, where it is stored at a controlled temperature to preserve its flavor and consistency. While the hazelnut paste is being prepared, the other ingredients are processed in parallel. Sugar, which provides sweetness to Nutella, is delivered to the factory in bulk containers or tankers. Upon arrival, the sugar is unloaded into silos, equipped with pneumatic conveying systems. These systems use air pressure to transport the sugar from the silos to the milling area, where it is ground into a fine powder. Industrial sugar mills are used for this purpose, and the grinding process ensures that the sugar particles are small enough to dissolve uniformly in the mixture. The factory also incorporates sieving systems to filter out any impurities or oversized sugar particles before they proceed to the blending stage. Cocoa powder, another key ingredient, undergoes a similar process. The cocoa powder is stored in sealed silos to protect it from moisture and contamination. Before being added to the Nutella mixture, the cocoa powder is sifted through vibrating screens to break up clumps and ensure a fine, even consistency. This step is crucial for achieving the smooth texture of the final product, as any clumps could create inconsistencies during blending. Palm oil, which gives Nutella its creamy consistency and prevents separation, is stored in large, temperature-controlled tanks. These tanks are equipped with heating elements to keep the oil in a liquid state, as palm oil tends to solidify at room temperature. The oil is pumped through insulated pipes to the mixing area, where it is carefully measured and added to the blend. The precise control of temperature and flow rate is essential to ensure that the oil integrates smoothly with the other ingredients. Skim milk powder, which adds a subtle dairy flavor and contributes to the creamy texture of Nutella, is stored in sealed containers or silos to prevent exposure to air and moisture. Before being used, the milk powder is sifted and screened to remove any lumps. Factories use advanced pneumatic conveying systems to transport the milk powder from the storage silos to the mixing area, ensuring that the ingredient is handled efficiently and hygienically. The blending process is the heart of Nutella's production, where all the prepared ingredients come together to form the final product. The blending tanks used in Nutella factories are massive, often with capacities of several thousand gallons. These tanks are equipped with high-speed agitators and temperature control systems. The hazelnut paste, sugar powder, cocoa powder, skim milk powder, palm oil, and vanillin are added to the tank in precise proportions, which are controlled by computerized dosing systems. These systems are programmed to weigh and dispense each ingredient accurately, ensuring consistency across batches. During blending, the mixture is heated slightly to help the ingredients combine more effectively. The temperature is carefully monitored, as excessive heat could alter the flavor and texture of the product. The blending tanks are designed to ensure even mixing, with agitators that create a vortex to incorporate all the ingredients thoroughly. The result is a homogeneous mixture with a smooth, creamy consistency. Once the blending process is complete, the mixture undergoes a refining stage. Refining is a critical step that ensures the final product is free of any graininess. The refining process takes place in multi-stage roller mills, which are equipped with heavy-duty steel rollers. These rollers apply immense pressure to the mixture, reducing the particle size of any remaining solids to less than 20 microns. This process not only enhances the texture of Nutella, but also improves its spreadability. The roller mills are fitted with precision sensors that monitor the pressure and temperature during refining, ensuring optimal performance. After refining, the mixture is transferred to the conching stage. Conching is a process borrowed from chocolate manufacturing and involves agitating the mixture in large, heated tanks for several hours. This process helps to further smooth the texture and enhance the flavor of the spread by allowing volatile compounds to evaporate and by evenly distributing the fats and solids. The conching tanks are equipped with paddles or rollers that knead the mixture continuously. The temperature and duration of conching are carefully controlled, as over-conching could negatively affect the spread's consistency. The finished Nutella is then pumped into holding tanks, where it is kept at a controlled temperature until it is ready for packaging. These tanks are equipped with agitators to prevent separation and maintain the spread's uniformity. Before the Nutella is packaged, it undergoes a final round of quality control. Samples from each batch are tested for flavor, texture, color, and viscosity. The factory uses advanced laboratory equipment such as viscometers and spectrophotometers to ensure that the product meets the company's stringent standards. Any deviations from the desired specifications are identified and corrected before the product proceeds to the packaging stage. Packaging is the final step in Nutella's production process, and it is carried out with the same level of precision and efficiency as the earlier stages. The spread is pumped from the holding tanks into automated filling machines, which dispense precise amounts of Nutella into jars. The filling machines are equipped with high-speed nozzles that can fill hundreds of jars per minute. Each jar is made from food-grade plastic or glass and arrives at the factory pre-sterilized to ensure hygiene. The jars are sealed with tamper-proof lids, which are applied and tightened using automated capping machines. Once the jars are sealed, they are conveyed to labeling stations, where Nutella's iconic branding is applied. The labels include important information such as the lot number, production date, and expiration date, which are printed using high-speed inkjet or laser printers. After labeling, the jars are inspected by vision systems that check for defects such as misaligned labels or damaged seals. Any defective jars are automatically removed from the production line. The jars are then packed into cardboard cartons using robotic packing systems. These systems are programmed to arrange the jars in specific configurations to maximize space and protect the jars during transportation. The cartons are sealed and stacked onto pallets using robotic palletizers. The pallets are then wrapped in plastic film for stability and loaded onto trucks or shipping containers for distribution. The entire packaging process is designed for high efficiency, with minimal manual intervention and maximum output. Throughout the factory, automation plays a key role in maintaining efficiency and consistency. Programmable logic controllers and supervisory control and data acquisition systems are used to monitor and control every aspect of the production process. These systems provide real-time data on parameters such as temperature, pressure, and flow rates, allowing operators to make adjustments as needed. The factory is also equipped with advanced robotics and machinery that ensure smooth operation, from ingredient handling to final packaging. Hygiene and safety are top priorities in Nutella factories. Production areas are constructed with food-grade stainless steel surfaces and epoxy-coated floors that are easy to clean and sanitize. Air filtration systems maintain a clean environment by preventing airborne contaminants from entering critical zones. Employees follow strict hygiene protocols, including wearing protective clothing and washing their hands regularly. The factory is regularly inspected to ensure compliance with international food safety standards, guaranteeing that every jar of Nutella is safe for consumption. This intricate, highly automated process ensures that Nutella is consistently smooth, flavorful, and delicious, meeting the high expectations of its millions of fans worldwide. Every step, from the handling of raw ingredients to the final packaging, is a testament to the engineering and precision that go into creating this beloved spread. The result is a product that continues to delight consumers, one jar at a time. Peanut butter, a staple spread beloved worldwide for its creamy or crunchy texture, requires a sophisticated and highly organized manufacturing process to meet the demand for consistent quality and flavor. Behind every jar of peanut butter is an intricate factory process that starts with the raw peanuts and ends with precisely packaged jars ready for distribution. Let's take an in-depth look at the factory production process, exploring the machines, systems, and engineering techniques that make it all possible. The process begins with the sourcing of raw peanuts. These peanuts are typically grown in countries like the United States, China, India, and Argentina, which are among the largest producers of peanuts globally. Peanuts are harvested in vast quantities, cleaned and dried at their source before being shipped to peanut butter manufacturing facilities. Factories require a consistent supply of high-quality peanuts, and to ensure that the raw peanuts are often tested upon arrival for size, moisture content, and overall quality. This ensures only the best peanuts are used for processing. Upon arrival at the factory, peanuts are stored in massive silos or bins designed specifically for food products. These silos are constructed from food-grade stainless steel or coated steel to prevent contamination and ensure proper hygiene. Inside the silos, the peanuts are protected from moisture, pests, and temperature fluctuations. These storage systems are equipped with conveyor systems that efficiently transfer peanuts from the silos to the initial cleaning and processing stages. The first step in processing peanuts is cleaning. Even though peanuts are partially cleaned at their source, factories implement a rigorous cleaning process to ensure no foreign materials or impurities remain. Vibrating screens are used to remove debris such as dirt, stones, and small sticks. Air classifiers blow air through the peanuts to remove lighter debris such as peanut skins or husks. Magnets are also employed to extract any metallic impurities. Optical sorting machines equipped with cameras and sensors scan each peanut as it moves along a conveyor belt, automatically removing any defective peanuts, including those with discoloration, mold, or deformities. After the cleaning process, the peanuts proceed to the roasting stage. Roasting is a critical step in peanut butter production, as it develops the rich, nutty flavor that defines the final product. Factories use industrial roasting ovens to roast the peanuts at controlled temperatures. These ovens come in two main types: batch roasters and continuous roasters. Batch roasters are used for smaller production lines, while continuous roasters, which use conveyor belts to move peanuts through a heated chamber, are used for larger scale operations. The temperature in these roasters typically ranges from 300 to 350 degrees Fahrenheit. The roasting process is closely monitored with temperature sensors and automated control systems to ensure the peanuts are roasted evenly. If some peanuts are over-roasted, they can turn bitter, while under-roasted peanuts may lack flavor. The level of roasting can also be adjusted depending on whether the final peanut butter will have a mild or more robust taste. Once roasted, the peanuts are cooled to stop the cooking process. Cooling is achieved by passing the roasted peanuts through chambers with powerful fans or cool air blowers. This step is crucial because it prevents the peanuts from continuing to cook, which could lead to inconsistencies in flavor. Some factories also use a water spray system to rapidly cool the peanuts, though this is less common as it can add moisture to the product. The cooling systems are designed to operate continuously to keep pace with the output of the roasting ovens. With the peanuts roasted and cooled, the next step is to remove their skins and separate the kernels. Skin removal is done using blanching machines. These machines have rotating drums or abrasive rollers that rub the peanuts, causing the thin outer skin to flake off. Some systems use steam blanching, where the peanuts are exposed to high-pressure steam to loosen the skins before mechanical removal. After blanching, the peanuts pass through air classifiers that blow away the loose skins, leaving behind clean peanut kernels. Factories also use gravity separators to sort peanuts by size and density, ensuring that only uniform peanuts proceed to the grinding stage. Before grinding, the peanuts are inspected again for quality. This is done using high-speed optical sorters that ensure any remaining defective peanuts are removed. Factories often have automated weighing and proportioning systems at this stage to determine the exact amount of peanuts needed for each batch. This level of precision is crucial for maintaining consistency in the flavor and texture of the peanut butter. The grinding process is the heart of peanut butter production. The roasted peanuts are fed into industrial grinders, where they are crushed into a fine paste. This process happens in multiple stages, beginning with coarse grinding and followed by finer grinding. The equipment used for this includes hammer mills and roller mills, which are specifically designed to reduce the peanuts into small, uniform particles. In many factories, the particle size is reduced to less than 20 microns, which is smaller than the diameter of a human hair. Achieving such a fine consistency is essential for the creamy texture that many consumers expect from peanut butter. For crunchy peanut butter, the process is slightly different. In these cases, a portion of the peanuts is coarsely ground and set aside before the final blending stage. These larger peanut pieces are later mixed into the smooth paste to create the characteristic crunchy texture. To prevent the peanut butter from separating, stabilizers such as hydrogenated vegetable oils or palm oil are added during the grinding process. These oils help bind the natural peanut oils to the solid peanut particles, ensuring a smooth and stable product that doesn't separate in the jar. Salt and sugar are also added at this stage to enhance the flavor of the peanut butter. Factories use precision dosing systems to measure and add these ingredients in exact proportions, ensuring every batch has the same taste. After grinding, the peanut butter is sent through a mixing stage, where it is further blended in large stainless steel tanks equipped with high-speed agitators. This stage ensures that the stabilizers, salt, and sugar are evenly distributed throughout the peanut butter. These tanks are often heated slightly to keep the peanut butter at the right consistency for mixing. The temperature is carefully controlled, as overheating can alter the flavor or texture of the peanut butter. Once the mixing is complete, the peanut butter undergoes quality control checks. Samples from each batch are tested in an on-site laboratory for flavor, texture, and consistency. Advanced instruments, such as viscometers, are used to measure the viscosity of the peanut butter, ensuring it meets the desired standards. Factories also use particle size analyzers to confirm that the peanut butter's texture is smooth and uniform. These quality checks are critical, as even slight variations can impact the final product's appeal to consumers. The final step in the manufacturing process is packaging. The peanut butter is pumped from the mixing tanks to filling machines, where it is dispensed into jars. These filling machines are capable of handling thousands of jars per hour, ensuring high efficiency. The jars, typically made of food-grade plastic or glass, arrive at the factory pre-cleaned and are sterilized again before filling. The filling nozzles are designed to dispense precise amounts of peanut butter into each jar, ensuring uniform weight and volume. Once the jars are filled, they move to the capping machines, where tamper-proof lids are applied and tightened. After capping, the jars are conveyed to labeling machines, which apply the brand's signature labels, along with lot numbers and expiration dates for traceability. Vision systems inspect each jar to ensure that the labels are correctly applied and that there are no defects in the seals or packaging. The jars are then packed into cardboard boxes using robotic packing systems. These robots are programmed to arrange the jars in specific configurations to optimize space and protect the jars during transportation. The boxes are sealed and stacked onto pallets using automated palletizing systems. Finally, the pallets are wrapped in plastic film for stability and loaded onto trucks or shipping containers for distribution. Throughout the entire production process, automation plays a vital role in maintaining efficiency and consistency. Factories are equipped with programmable logic controllers, PLCs, and supervisory control and data acquisition, SCADA systems, that monitor and control every aspect of production. These systems provide real-time data on parameters such as temperature, pressure, and flow rates, allowing operators to make adjustments as needed. Robotic systems handle many tasks, from sorting and cleaning peanuts to packaging the final product, reducing the need for manual labor and ensuring precision. Hygiene and safety are also top priorities in peanut butter factories. The production areas are constructed with food-grade stainless steel surfaces and epoxy-coated floors that are easy to clean and sanitize. Positive air pressure systems prevent airborne contaminants from entering critical zones, while strict hygiene protocols ensure that employees maintain cleanliness throughout the production process. The entire facility is regularly inspected to comply with international food safety standards, ensuring that every jar of peanut butter is safe for consumption. Peanut butter production is a complex and highly technical process that relies on advanced machinery, precise engineering, and rigorous quality control. From the cleaning and roasting of peanuts to the grinding, mixing, and packaging of the final product, every step is designed to create a spread that is smooth, flavorful, and consistent. Factories operate with remarkable efficiency, producing thousands of jars per day to meet the global demand for this versatile and beloved product. Strawberry jam production is a fascinating and highly engineered process that combines precision machinery with time-tested techniques to create a smooth, fruity spread. At the core of this process are high-quality strawberries, sugar, pectin, and citric acid, all carefully handled and processed to achieve the perfect consistency and flavor. Inside a modern jam factory, every step is optimized for efficiency, consistency, and food safety. The process begins with the selection and delivery of fresh or frozen strawberries. Factories typically source strawberries from local farms or large-scale suppliers. Frozen strawberries are often preferred for large-scale production because they are preserved at peak ripeness, ensuring consistent flavor year-round. The strawberries arrive in bulk containers and are stored in cold rooms or freezers to maintain their quality until processing begins. Before entering the production line, the fruit undergoes a thorough cleaning process. This includes washing the strawberries in large tanks filled with filtered water, where gentle agitation removes dirt, debris, and any residual pesticides. Once cleaned, the strawberries pass through optical sorting machines. These machines use cameras and sensors to identify and remove defective or discolored fruit. Advanced systems can even detect minute imperfections, ensuring that only the highest quality strawberries make it into the jam. After sorting, the strawberries are sent to cutting or mashing machines, depending on the desired jam texture. For chunkier jams, strawberries are coarsely chopped, while for smooth spreads, they are mashed or pureed into a uniform consistency. The fruit then enters large stainless steel cooking kettles or continuous cooking systems. In these vessels, the strawberries are combined with sugar, which not only sweetens the jam, but also acts as a natural preservative. The sugar is added using automated dosing systems that measure precise quantities to ensure consistent flavor. Pectin, a natural thickening agent derived from fruit, is added to help the jam set. Citric acid is also incorporated to balance the sweetness and enhance the fruit's natural flavor. The mixture is slowly heated, with temperatures reaching up to 220 degrees Fahrenheit to activate the pectin and achieve the ideal gel-like consistency. During cooking, the jam undergoes constant agitation to prevent scorching and ensure even heating. Steam-jacketed kettles or vacuum cookers are often used, as they allow for rapid and uniform heating. Modern vacuum systems are particularly advantageous because they enable cooking at lower temperatures, preserving the fresh flavor and bright color of the strawberries. Throughout the cooking process, sensors monitor the temperature, pH levels, and viscosity of the jam, ensuring that the final product meets strict quality standards. Once the jam reaches the desired consistency, it is pumped through a series of filters to remove any seeds or large pieces if a smoother texture is desired. The finished jam is then transferred to filling machines. These machines dispense precise amounts of jam into sterilized glass jars or plastic containers. The jars are immediately sealed with tamper-proof lids to maintain freshness and prevent contamination. After sealing, the jars are passed through pasteurization tunnels, where they are briefly heated to destroy any remaining microorganisms. Finally, the jars are labeled, inspected, and packed into cartons using robotic packaging systems. The entire process is highly automated, ensuring efficiency and consistent quality, from the arrival of fresh strawberries to the delivery of jars to store shelves. This seamless blend of traditional cooking techniques and advanced technology ensures that every jar of strawberry jam is rich in flavor, perfectly textured, and safe for consumers to enjoy. In a modern Oreo manufacturing facility, key dry ingredients are delivered in bulk, often by rail cars or food-grade trucks, and are pneumatically conveyed into large storage silos made of stainless steel or epoxy-lined carbon steel. These silos are sealed from air and moisture and are connected to the factory's central control system. The main dry ingredients include unbleached, enriched wheat flour, processed cocoa powder, granulated sugar, and minor dry components like baking soda and salt. Each of these materials is handled in its own silo or hopper, and automated augers or vibratory feeders dispense precise quantities into batch weighing hoppers. These hoppers sit on load cells, sensitive scales that can measure down to a fraction of a gram. This is essential because the correct ratio of flour to cocoa to sugar directly affects not only the flavor, but also how the dough behaves under pressure during molding. If the cocoa content is even slightly too high, for instance, the dough may become too brittle and crack during forming. If it's too low, the wafers may bake up too soft, losing the crisp snap that defines an Oreo. Once the dry materials are batched, they are conveyed into a pre-mixing chamber. At this stage, powdered ingredients are briefly tumbled together to ensure initial homogeneity before liquids are added. Then it's time for the liquid components to enter the system. These include vegetable shortening, often a blend of palm and canola oil, along with a sugar syrup or glucose solution, invert sugar, lecithin, and vanillin or other flavoring agents. The fats and liquids are stored in temperature-controlled tanks and are metered into the mixer through heated pipes. The temperature of the fats is critical. Too cold, and they won't disperse evenly. Too hot, and they could melt too aggressively, breaking down the emulsion and affecting dough integrity. All of these components are combined in large jacketed horizontal mixers or double sigma arm batch mixers. These mixers are chosen for their ability to handle heavy, cohesive doughs while still ensuring thorough dispersion. Inside the mixer, paddles or blades knead the dough continuously, folding and stretching it to develop a uniform texture. The mixer operates under a specific time and speed profile, starting slow to incorporate the dry and wet components, then increasing speed to blend, then finishing with a gentle knead to avoid overworking the dough. The goal here is a dough that's soft but not sticky, cohesive but not tough. Sensors inside the mixing chamber monitor temperature and torque, two key indicators of dough readiness. If the dough becomes too warm from friction, it can become greasy and difficult to form clean edges in the molding machines. If it's undermixed, the ingredients won't be uniformly distributed, and inconsistencies in cookie size, color, and bake profile will result later on. Once the dough reaches its target specifications, it's discharged from the mixer through a hydraulically controlled trapdoor at the base of the mixing tank. The dough falls into a dough transport system, typically a set of conveyors or troughs lined with non-stick materials like Teflon or food-grade UHMW polyethylene. At this stage, the dough may still be slightly warm, around 30 degrees Celsius to 35 degrees Celsius, and has a dense, matte appearance with a strong cocoa aroma. Before moving to the forming machines, the dough must undergo a resting period in certain operations. This allows the flour to fully hydrate and any residual gases or trapped air to escape. In high-speed production environments, however, this rest period may be minimized or skipped altogether if the formulation is optimized for immediate processing. This completes the initial phase: ingredient intake, formulation, mixing, and dough discharge. Each step up to this point is carefully controlled by recipe management software that ensures no human error can affect batch consistency. Recipe locks, scanner-based operator identification, and redundant scale verification ensure each batch of Oreo wafer dough is made precisely to the specifications required to perform flawlessly in the next stage of the journey: shaping and embossing. Now that the chocolate wafer dough has been prepared with absolute precision, measured, mixed, and conditioned, it moves into one of the most visually iconic and mechanically fascinating phases in the Oreo production line: forming and molding. This step takes the dense, cocoa-rich dough and transforms it into thousands of uniformly sized, detailed cookie wafers, each embossed with the distinctive Oreo pattern. This is not simply cutting shapes out of dough, it's a highly engineered, high-speed process where consistency in shape, thickness, and surface detail must be maintained across millions of units every day. The freshly prepared dough is conveyed to a hopper positioned above a sheeter. This sheeter is a wide, stainless steel roller assembly that flattens the dough into a uniform sheet of specific thickness. The dough moves between a set of rollers, typically 2 or more steel cylinders calibrated to exact tolerances that compress it to the target height. For Oreo wafers, the final sheet is quite thin, often around 3 to 4 millimeters, with a consistent density and moisture distribution. Getting this thickness right is critical. If the sheet is too thick, the cookie may not bake evenly or could become too brittle. Too thin, and the cookies may crack, burn, or crumble during sandwiching. Sensors measure the thickness of the sheet continuously using laser or ultrasonic gauges. If deviations are detected, servo-driven actuators automatically adjust roller spacing to maintain precision. The sheeter also includes edge trimmers, small, motorized blades that cut off uneven or frayed edges of the dough sheet to keep the line uniform. The trimmed edges are collected by a scrap recovery system and reintroduced into the mixing system, minimizing waste without compromising freshness or quality. Once the dough sheet is perfected, it enters the rotary molder. This machine is central to the Oreo brand's identity, as it forms the shape, size, and embossed design of each cookie wafer. The rotary molder consists of 2 primary components, a rotating die roller and a pressure roller. The die roller is a cylindrical drum engraved with multiple cavities, each one precisely carved with the Oreo design. These cavities aren't just cosmetic. Their depth and contour dictate the final relief of the cookie surface. As the dough sheet passes between the die roller and pressure roller, each cavity punches into the dough, compressing it into shape and imprinting the Oreo design. The pressure roller, covered in food-safe rubber or polymer, pushes the dough up into the die cavities, ensuring a clean, complete mold. As the die drum continues rotating, the shaped wafers are extracted by a combination of mechanical pushes and vacuum assist systems, which gently remove the cookies from the cavities without smudging the design. These freshly molded cookie wafers are then transferred onto a wide mesh conveyor belt in a continuous, uninterrupted line. Each wafer is spaced evenly to allow for proper airflow in the next phase, baking. Meanwhile, the excess dough surrounding the cutouts, known as webbing, is carefully separated and sent back through the scrap system. This recovery loop is highly efficient, capturing nearly 100% of the unused dough and returning it to the mixer via chilled transport belts. To ensure product consistency, reworked dough is blended at a fixed percentage into fresh dough, preventing any changes in texture, flavor, or moisture that might result from overprocessing. As the line of uniform, molded Oreo wafers advances, they approach the baking tunnel, one of the most thermodynamically sophisticated parts of the facility. The tunnel oven is a massive structure, often exceeding 30 meters in length, segmented into multiple temperature-controlled zones. Each zone is precisely tuned to manage the gradual dehydration and expansion of the cookie, ensuring even baking from edge to center. The ovens use convection, conduction, and in some cases, radiant heat, depending on the equipment manufacturer and regional factory specifications. The cookie wafers bake as they travel slowly through the tunnel, typically for a duration of 4 to 6 minutes. Conveyor speed, airflow rate, and internal oven temperatures are continuously adjusted via programmable logic controllers that interface with sensors monitoring internal humidity, surface temperature, and even color of the baking cookies using infrared imaging systems. The target bake is one where the cookie becomes crisp and fully set while retaining a slight moisture gradient at its core, enough to ensure it sandwiches cleanly without shattering, and holds up in milk without becoming soggy too quickly. Another crucial parameter monitored at this stage is cookie spread and diameter. Because the molded wafers expand slightly as they bake, their final size must fall within a fraction of a millimeter to ensure they'll match perfectly with their paired half during sandwiching. Edge blowout, where cookies develop uneven bulges or bubbles, is prevented by careful control of initial dough temperature, mold compression depth, and oven humidity during the first baking phase. As the cookies exit the oven, they are immediately passed through a staged cooling system. This phase is designed to gently bring the cookies from their internal post-bake temperature of roughly 160 degrees Celsius down to ambient room temperature. Cooling too quickly can cause the wafers to crack, warp, or experience checking, tiny surface fractures that affect aesthetics and structural integrity. To avoid this, the conveyor slowly moves the wafers through a series of cooling zones with progressively decreasing airflow temperatures. High-volume fans push filtered, dehumidified air over the wafers in a cross-flow pattern that cools them evenly on all sides. By the time the wafers reach the end of the cooling tunnel, they are firm, crisp, and at a stable moisture level, typically around 1.5% to 2%. This ensures maximum shelf life, a satisfying crunch, and ideal compatibility with the creme filling in the next phase of production. They are now ready for alignment and pairing. Wafers are automatically aligned into dual streams using diverters and channeling guides. Conveyor belts equipped with vision systems scan for defects such as missing embossing, chips, discoloration, or breakage. These systems use high-speed cameras and AI-assisted pattern recognition to detect any imperfections in milliseconds. Rejected cookies are diverted to a waste collection hopper, and approved wafers continue forward to the sandwiching stage. With the Oreo chocolate wafer cookies fully formed, baked, and cooled, the production line now transitions into one of the most iconic and mechanically synchronized parts of the process: sandwiching. This stage involves the precise alignment of two delicate wafer halves around a carefully deposited swirl of creme filling, forming the complete Oreo cookie as we know it. What may seem like a simple task, placing filling between two cookies, is in fact a highly controlled and technically advanced process that prioritizes speed, accuracy, hygiene, and product consistency. The cooled wafers arrive at the sandwiching station via dual-lane conveyors that separate and feed cookies into two different orientations: bottom wafers and top wafers. The bottom wafers are destined to receive the cream filling, while the top wafers are held back momentarily, synchronized to arrive just as the filling has been deposited. Vision-guided pick-and-place arms or mechanical guides ensure that each cookie is properly positioned and oriented with the embossed design facing upward, especially important for branded recognition in the final presentation. The placement needs to be exact. Even a slight misalignment could result in uneven sandwiching or a crooked creme center, which would be rejected downstream. At the heart of the sandwiching line is the creme depositor. This component is engineered to dispense a precise amount of creme onto the center of each bottom wafer. The creme filling itself has been prepared earlier in the process and is stored in stainless steel holding tanks near the sandwiching line. The base creme is a blend of vegetable shortening, powdered sugar, and natural or artificial flavorings, aerated to achieve a smooth and creamy texture. It is kept at a controlled temperature, typically between 25 degrees Celsius and 30 degrees Celsius, to maintain flow consistency without being too runny or too firm. The creme is pumped into the depositor through a jacketed delivery line, which maintains temperature and prevents any hardening or separation. Inside the depositor, a rotary valve system or piston-driven nozzles release measured quantities of filling in circular swirls directly onto each passing wafer. The target deposition amount is extremely precise, usually around 3 grams per cookie for the original Oreo. For double stuff, the system is calibrated to deliver twice that volume, and the depositor nozzle height is adjusted accordingly to accommodate the larger swirl. The deposition speed is synchronized with the conveyor, meaning each swirl is deposited while the bottom wafer is in motion. To maintain consistent swirl shapes, the nozzle spins at a high RPM as it dispenses the cream. Sensors and imaging software track swirl size, height, and position. If the deposit strays from the central zone or falls outside weight tolerances, that cookie is automatically flagged and diverted. These sensors run continuously, sampling thousands of cookies per minute with extremely tight thresholds for variance. Once the creme is in place, the top wafer is gently placed onto the swirl. This is done by an overhead transfer arm or drop chute designed to lower each top cookie into place with just enough pressure to make contact without squashing the filling. The timing here is critical. Placing the top wafer too early could create smearing or incomplete adhesion, while placing it too late could allow the creme to set and result in a loosely held sandwich. Once the two halves make contact, a calibrated compression roller or paddle gently presses them together to create a uniform sandwich with a visible, even creme edge. The newly assembled Oreo cookies are then conveyed forward to undergo another round of quality inspection. At this stage, high-speed vision systems again scan for defects. These include cracked or broken wafers, misaligned sandwiches, off-center cream, or excess filling that has oozed out past the edges. Cookies that fail to meet standards are ejected via pneumatic pushers or retractable gates, landing in separate bins for non-conforming product. These rejected cookies are either discarded or recycled depending on factory policies and whether they passed earlier food safety checks. The good cookies move on to the next major phase, cooling and setting. Even though the creme filling is solid at room temperature, the act of depositing and sandwiching generates residual warmth, and the filling remains somewhat malleable for several minutes. To stabilize the sandwich structure and ensure long-term integrity during packaging and shipping, the cookies are passed through a controlled cooling tunnel. This tunnel gradually brings the product's temperature down to a stable point, typically just below ambient, which firms up the cream and locks in the sandwich's structural cohesion. As cookies exit the cooling tunnel, they are directed toward the packaging line. Here, the cookies are grouped and arranged into stacks or rows depending on the intended package format, whether it's a classic tray-style retail pack, a resealable pouch, a single-serving sleeve, or a multi-pack unit. For traditional packs, the cookies are guided into channels that group them into stacks, typically of 3 or more, which are then lowered into thermoformed plastic trays by robotic pick-and-place units. These trays help protect the cookies from damage and keep them organized for end-user convenience. Parallel to this, packaging film, pre-printed with branding, nutritional labels, and product information, is unwound from large rolls and fed into a form-fill seal machine. As the cookie-filled trays pass through the machine, the film is wrapped around the product, heat-sealed on all sides, and trimmed to size. Oxygen scavengers or desiccants may be inserted for freshness in some markets, depending on climate and shelf life requirements. For resealable packs, a Ziploc or peel-back adhesive strip is applied as part of the film sealing process, ensuring that consumers can open and close the package without reducing freshness. Each package unit is printed with a lot number, manufacturing date, facility code, and expiration date using high-speed thermal inkjet or laser printers. These codes enable full traceability and are cross-referenced with the production batch data stored in the factory's ERP system. From mixing and molding to creme filling and sealing, every step of the process can be traced back to specific machines, operators, shift schedules, and ingredient batches, an essential feature for food safety compliance and recall readiness. Once sealed, packages are conveyed to automated case packers. Here, robotic arms load the wrapped units into corrugated cardboard cartons, which are then glued or taped shut. These cartons are palletized according to preset patterns that optimize load stability and cube efficiency for shipping. Pallets are wrapped with stretch film, labeled with shipping barcodes and inventory data, and routed to the warehouse staging area. At this point, the Oreo cookies have completed their physical transformation from separate cocoa wafers and creme filling into a polished, fully packaged, ready-to-ship product. But before they leave the factory, they undergo a final quality audit. Samples from each batch are pulled from the finished goods line and tested by in-house sensory panels and laboratory staff. Taste, texture, aroma, appearance, and moisture content are evaluated to ensure that the product not only looks perfect, but delivers the consistent flavor and mouthfeel that Oreo is known for. Moisture levels are especially critical. Too high, and the cookie can lose its crispness during storage. Too low, and it can become brittle or stale. Texture analyzers apply mechanical pressure to the cookies to evaluate crunch resistance and breaking force, while gas chromatography is used to verify flavor compound profiles. Packaging integrity tests include drop tests, seal strength verification, and temperature cycling simulations that mimic transport and storage conditions across various markets. Once these final inspections are passed, the cookies are released for distribution. Pallets are loaded into climate-controlled trucks or containers, routed through regional distribution centers, and ultimately arrive at retail outlets, vending networks, or direct-to-consumer channels. With the Oreo cookie now fully assembled, inspected, packaged, and palletized, the final phase of the in-factory process is dedicated to the logistics, storage, inventory control, and outbound quality assurance systems that prepare the product for global distribution. While it may seem like the technical complexity is behind us, this stage involves its own set of sophisticated workflows designed to ensure that every package remains pristine, traceable, and shelf-stable for months after production, regardless of whether it ends up in a small, rural convenience store or a high-volume urban supermarket. The finished pallets of Oreos are moved from the end-of-line palletizing systems into a dedicated finished goods warehouse. This space is part of the factory complex, but isolated from production to prevent cross-contamination and maintain temperature and humidity stability. Oreo cookies, especially those with creme fillings, are highly sensitive to environmental changes. Excessive heat can soften the filling or compromise the packaging seal, while high humidity can cause moisture migration into the wafer, leading to loss of crispness. To combat these risks, the warehouse is maintained at a tightly regulated temperature, typically between 18 degrees Celsius and 22 degrees Celsius, with relative humidity kept under 50%. The facility is segmented into climate zones for different packaging formats, with certain areas reserved for international shipments that may require added humidity resistance or longer storage durations. Air handlers, industrial-grade dehumidifiers, and air filtration systems constantly regulate and cycle the air to maintain these parameters. Even the lighting systems are designed to minimize UV exposure, which could, over time, degrade packaging ink or food contact films. Once inside the warehouse, each pallet is scanned and logged into a warehouse management system. This system is fully integrated with the factory's enterprise resource planning software and allows operators to track not only where each pallet is stored, but exactly what production line, time, and ingredient lot was used to produce its contents. Each pallet label includes a unique serial number, barcode, and QR code that links to this full production history. This traceability is essential not just for internal logistics, but also for compliance with food safety regulations around the world, which require manufacturers to be able to track every product from raw ingredient to final point of sale. The WMS automatically arranges pallets by product type, batch date, and destination. Those scheduled for export may be routed to a separate staging zone where they will be checked for compliance with international packaging laws. Different markets may require translated labels, adjusted nutritional formats, or modified lot codes. Some export destinations also require additional tests, such as microbial swabs or accelerated shelf life sampling, to meet foreign government regulations. These are performed in an adjacent quality control annex, and only upon clearance are these pallets released to outbound logistics. Before any Oreo shipment leaves the facility, it undergoes a final visual inspection for physical damage to packaging, tamper seals, and box integrity. Any visible damage may indicate mishandling during internal transit or weak spots in pallet stability. Operators are trained to look for warped trays, compromised seals, or even small tears in the flow wrap film that could affect product freshness. Should any defect be discovered, that pallet is held for secondary inspection, and depending on severity, it may be repackaged or scrapped entirely. At this point, logistics coordinators use automated routing systems to schedule outbound shipments. These systems factor in geographic location, delivery deadlines, climate conditions, and truck availability. For example, shipments bound for warmer climates during the summer may be prioritized for insulated or refrigerated trucks to prevent the creme from softening. Long-haul shipments may be routed through distribution centers that offer cross-docking or climate-controlled storage to preserve product quality along the supply chain. The loading dock itself is operated with precision. Trucks arriving at the facility must be cleaned, inspected, and approved before any Oreo products are loaded. This includes visual inspection for pests, residue from prior shipments, and confirmation that the trailer temperature is within specification. Only after a truck passes these inspections does the facility open the dock door and begin the loading sequence. Robotic forklifts or human operators load the pallets according to pre-planned diagrams that ensure weight is evenly distributed and product is easily accessible at the destination. Each shipment is logged with time, driver ID, carrier information, route ID, and estimated delivery window. Once loaded, trucks are sealed with tamper-evident locks and dispatched with digital shipping documents, including delivery confirmations and scanned QR codes for receiving teams. The WMS updates the ERP system in real time, closing the inventory loop and marking the batch as shipped. This inventory and logistics traceability is crucial for meeting compliance with global food safety standards like the Global Food Safety Initiative, hazard analysis, and critical control points, and ISO 22000. Even after the Oreo product leaves the plant, the factory remains connected to its life cycle through digital feedback systems. Retailers and distributors have access to portal-based interfaces where they can report damages, delayed deliveries, or unexpected inventory issues. Returned products are scanned upon arrival at reverse logistics zones where factory staff investigate issues, analyze production records, and determine root causes. In cases where errors are found, such as premature staleness, flavor imbalance, or packaging failure, continuous improvement protocols are triggered to address the upstream causes. While these systems function to protect the product, they also feed into a broader factory goal: performance analytics and continuous optimization. The data from every shipment, temperature logs, shipping duration, breakage rates, seal integrity, and even consumer complaints is compiled into dashboards reviewed weekly by production leads, QA managers, and logistics coordinators. These dashboards enable the factory team to track KPIs like OTIF, defect per million rates, inventory turnover, spoilage reduction, and carbon footprint per pallet. Some Oreo plants are moving even further towards sustainability at this stage of production. Cardboard shipping boxes are made with recycled content and are themselves fully recyclable. Pallet wrap films are being downgauged or replaced with biodegradable alternatives. Facilities are experimenting with hybrid electric fleet partnerships or rail transport instead of trucks to reduce emissions. In select markets, even the plastic trays inside Oreo packs have been redesigned for recyclability, and clear labels now inform consumers on proper disposal. It begins at nearly freezing temperatures, with a roar of compressors and a hiss of chilled air. In a modern ice cream factory, the sweet smell of vanilla mixes with the sharp tang of disinfectant, and somewhere in the maze of pipes and stainless steel tanks, milk begins its transformation into something that millions of people crave every single day. What's astonishing is how much engineering hides behind something so simple. A scoop of ice cream looks innocent, but it's really the result of physics, chemistry, and some of the most precise temperature control on Earth. At the start of the process, raw milk arrives in tanker trucks, still cold from the dairy farms. Each load is tested for purity, fat content, temperature, and bacterial count before it's allowed anywhere near the production floor. This is the first line of defense. Once it passes inspection, the milk is pumped into enormous chilled silos, towering tanks that can each hold tens of thousands of liters. From there, it's blended with cream, sugar, and a secret mix of stabilizers and emulsifiers. These aren't mystery chemicals. Think of them as the architects of texture. They keep the fat and water from separating, prevent ice crystals from getting too big, and give that signature creamy body that melts smoothly on the tongue. The blending happens in what's known as a mix tank, a gleaming, jacketed vessel where powerful paddles churn the ingredients together. The mixture, called the ice cream base, is heated to around 70 to 85 degrees Celsius for pasteurization. This step kills any microorganisms that might spoil the product, and it's a legal requirement in almost every country. But pasteurization does more than make it safe. It subtly changes the proteins in the milk, allowing them to bind better with water and fat later on. Within minutes, the sweet liquid goes from raw dairy to something closer to a rich custard. Next comes homogenization. This is where the mix is forced at high pressure, often around 2000 psi, through a narrow valve. The sheer force shatters the fat globules, breaking them into microscopic droplets that disperse evenly through the liquid. It's a mechanical miracle that ensures the ice cream will never taste greasy or separate into layers. Without homogenization, the final product would feel gritty and unstable. After the mix is pasteurized and homogenized, it's cooled rapidly down to about 4 degrees Celsius. Then it rests. This is called the aging phase. The tanks hold the mixture for anywhere between 4 and 12 hours. And while it just sits there, something remarkable happens at the molecular level. The fat begins to crystallize slightly, proteins and stabilizers fully hydrate, and the mix thickens to a silky consistency. Aging might not look exciting, but it's essential for texture. Skipping it can make ice cream feel thin and icy, no matter how good the ingredients are. Only after this quiet period does the action ramp up again. The aged mix is pumped into continuous freezers, massive steel cylinders that churn and freeze at the same time. Inside, a rotating dasher scrapes the inner walls while injecting air into the mix. This step, known as overrun, determines the lightness of the final product. Most commercial ice creams contain about 50 to 100% overrun, meaning the volume doubles due to tiny air bubbles trapped inside. Premium brands might use less air for a denser, creamier feel. The moment the base begins to freeze, usually within seconds, the temperature drops to around -5 degrees Celsius, and the texture changes from a thick custard to something resembling soft serve. It's not fully frozen yet. It's halfway between liquid and solid. That's when the fun additions come in. Pieces of chocolate, caramel swirls, crushed cookies, roasted nuts, whatever the recipe calls for, are fed through separate hoppers and augers that gently fold them into the semi-frozen stream. The machinery has to be incredibly precise here. Additions are metered by weight or volume, synchronized so the distribution stays uniform. Imagine a waterfall of cookie dough chunks tumbling into a ribbon of freezing cream, all timed to the millisecond. From there, the ice cream flows directly into filling machines. Depending on the product line, it could be portioned into tubs, cones, or novelty molds. For pints, automated nozzles swirl perfect ribbons into containers that travel on conveyors in tight formation. If it's a multi-flavor product, twin heads might layer chocolate and vanilla together in mesmerizing spirals. For ice cream sandwiches, robotic arms deposit precise slabs of ice cream between cookies before pressing and wrapping them in one fluid motion. Speed is crucial. The longer ice cream stays soft before hardening, the larger its ice crystals grow, which means a coarser texture later. To prevent that, factories use a process called shock freezing. The freshly filled containers are rushed through blast freezers where air circulates at temperatures as low as -40 degrees Celsius. Within minutes, the core temperature of each tub plunges to about -20. At that point, the ice cream's microscopic structure locks in place. Tiny crystals, stable fat droplets, evenly distributed air bubbles. That frozen architecture is what gives ice cream its creamy mouth feel even months later. Behind the scenes, the level of automation is staggering. Temperature sensors, flow meters, and computer-controlled valves orchestrate the movement of every batch. In a large facility, an operator can monitor dozens of tanks and freezers from a single control room, watching graphs of pressure and viscosity on glowing screens. When a line changes flavor, from vanilla to strawberry, for example, clean-in-place systems flood the entire circuit with hot water and sanitizer, flushing out every trace of the previous mix. Hygiene here is almost ritualistic. Workers wear hairnets, masks, and sanitized boots. Some areas require entering through air showers that blow off dust and lint. A stray speck of contamination could ruin thousands of liters of product. Even the air inside the factory is filtered. Ice cream attracts odor easily, so the production environment must stay neutral. Stainless steel surfaces gleam under bright lights, and floors slope gently toward drains for constant washing. Some plants clean continuously, cycling through disinfection routines every few hours. The smell that lingers isn't the sweetness of dessert, it's the faint metallic tang of sterilized equipment mixed with a whisper of dairy steam. Once the hardening stage is done, the ice cream enters packaging and cold storage. Robotic arms pick up the frozen tubs, apply lids and labels, then shrink wrap them into pallets. Everything moves fast because the cold chain must never break. If the ice cream warms even slightly, ice crystals can reform when it refreezes, ruining texture. Warehouses maintain constant sub-zero conditions, often around -25 degrees Celsius, while conveyors shuttle products toward loading docks. There, refrigerated trucks, sometimes hundreds per day, carry them to distributors and supermarkets. The logistics are choreographed down to the minute. Every container has a batch code, linking it back to the exact silo of milk and the moment it passed through pasteurization. One of the most fascinating engineering challenges is keeping consistency across seasons. Milk fat changes with a cow's diet, and sugar behaves differently at varying humidity levels. To keep the same texture and taste year-round, factories rely on sensors and chemical analysis to tweak formulas in real time. A computer might adjust the fat ratio or freezing time automatically, compensating for weather or ingredient variation. It's precision manufacturing disguised as dessert making. The journey from bean to bar is a story of controlled heat, relentless grinding, and molecular level precision. And it all begins with sorting. When the raw cocoa beans arrive, they don't look like the glossy, rich ingredient people imagine. They're dusty, uneven, and mixed with bits of stems and husks from the farms. Huge vibrating sieves shake them clean, separating out debris while compressed air blows away lighter fragments. Optical scanners sometimes join the process, identifying defective or moldy beans by color and rejecting them in a blur of air puffs. Then comes roasting, the most magical and arguably the most crucial step. The beans tumble in massive rotating drums, heated to anywhere between 120 and 160 degrees Celsius. The air smells incredible, like toasted nuts and caramelized sugar, with undertones of coffee and smoke. Inside each bean, heat triggers the Maillard reaction. Sugars and amino acids rearrange, releasing hundreds of aromatic compounds that define the flavor of chocolate. But there's an art to it. Too much heat, and the beans taste bitter. Too little, and they stay flat and earthy. The machines are programmed with precise curves, gradually ramping up and cooling down over about half an hour, ensuring every batch hits its flavor mark. After roasting, the beans must be cracked and winnowed. Industrial rollers crush them into small pieces called nibs, and powerful fans then separate the lighter husks from the heavier nibs. The husks are discarded or sometimes sold for brewing cocoa tea. What remains, the nib, is pure cocoa in solid form, containing roughly equal parts fat and solids. From this point forward, everything that makes chocolate irresistible is hidden inside those nibs. The nibs head into massive steel grinders. Under enormous pressure, granite or steel rollers crush them until the friction melts the cocoa butter inside. What starts as a dry crumb turns into a thick, glossy paste called chocolate liquor. Despite its name, there's no alcohol involved. Liquor just refers to its liquid state. This mixture is 100% pure cocoa, dark and intensely bitter. If you dipped a spoon into it, it would coat your tongue like molten fudge and leave behind a sharp, almost smoky aftertaste. Depending on what kind of chocolate is being made, this liquor is blended with sugar, milk powder, or extra cocoa butter. Dark chocolate may contain just cocoa liquor, cocoa butter, and sugar. Milk chocolate adds milk solids for creaminess. White chocolate skips the solids entirely, relying on cocoa butter, milk, and sugar for its pale color and delicate flavor. Each formulation is measured to the gram. Too much fat, and the chocolate won't set correctly. Too little, and it feels chalky. At this stage, the mixture still feels gritty. The particles of sugar and cocoa are too large for the silky melt that defines good chocolate. To fix that, it goes through refining. The mix passes between 5 or more steel rollers stacked vertically, each one turning faster than the one above it. The pressure crushes the particles down to just 15 to 25 microns, about 1/3 the width of a human hair. This is where texture is born. A well-refined chocolate feels smooth not because it's liquid, but because its solid particles are so small they slide across the tongue without resistance. Then comes the step that chocolatiers call conching, the heart of chocolate making. Huge open tanks filled with slowly stirring blades churn the refined chocolate for hours or even days. During this process, heat and movement drive off unwanted acids and moisture while coating each tiny particle with cocoa butter. The chocolate thickens, then gradually becomes smoother and more fluid. Imagine an ocean of molten chocolate rolling and folding over itself, releasing warm, sweet aromas as it matures. The sound of the machinery is low and rhythmic, like waves breaking in a metal bay. Modern conchers are temperature controlled to the degree. Dark chocolate might conch at around 80 degrees Celsius, while milk chocolate prefers slightly cooler conditions. Every manufacturer has its own secret curve for how long to conch. Some aim for 8 hours, others for 72. The longer it runs, the more mellow and complex the flavor becomes. It's part chemistry, part artistry. Once conching is complete, the chocolate is filtered and stored in heated tanks, still liquid, waiting for the most delicate phase of all, tempering. This is the step that decides whether the final bar will have a shiny snap or a dull, crumbly finish. Cocoa butter is a polymorphic fat, meaning it can solidify into several different crystal structures, but only one of them, the form vive crystal, gives that perfect glossy sheen and satisfying snap. Tempering is all about coaxing those crystals into existence. The chocolate is cooled from around 45 degrees Celsius down to 27, then gently warmed again to about 31. This process encourages stable crystals to form while eliminating unstable ones. Machines called temperers handle this automatically, circulating chocolate through heating and cooling zones while stirring continuously. The result is liquid chocolate that's glossy, smooth, and ready to mold, but chemically balanced to harden just right. Once tempered, the chocolate flows through pipes to the molding line. For bars, molds travel along conveyor belts under nozzles that deposit precise doses of liquid chocolate. Vibrating tables beneath the molds shake out air bubbles, creating that perfect, uniform surface. If it's a filled chocolate, say with caramel or praline centers, the process happens in layers. A thin shell is molded first, cooled to harden, then filled, and finally sealed with another layer of chocolate on top. Timing has to be flawless, so the layers bond seamlessly without melting into each other. In the next tunnel, the temperature drops sharply to set the chocolate. Chilled air, often around 10 degrees Celsius, flows over the molds as they pass through. Within minutes, the chocolate contracts slightly, loosening itself from the mold walls. A gentle tap or an automated arm releases each bar or praline onto a conveyor, glossy and flawless. The sound is oddly satisfying, a soft series of clicks as hundreds of pieces pop free. Before packaging, every batch undergoes inspection. Workers or cameras check for surface imperfections, color consistency, or bloom. Those white streaks that form if the tempering wasn't perfect. Any flawed pieces are melted down and recycled back into the process. Nothing goes to waste here. Even the aroma-filled air above the conches can be filtered to capture cocoa particles. The packaging area feels entirely different from the roasting room. It's cool, dry, and smells faintly of sugar and foil. Robotic arms wrap each bar in layers of film, foil, or paper at speeds so fast the movement blurs. Labels, codes, and seals are printed in real time, ensuring traceability from farm to shelf. Behind glass walls, automated systems slide the finished bars into cartons and then onto pallets bound for warehouses kept at strict temperature control, around 18 degrees Celsius, where chocolate remains stable and glossy. What makes chocolate manufacturing remarkable isn't just the machines, it's the precision of the environment. Humidity has to stay low, or the sugar can absorb moisture and form crystals. The temperature must never rise above 25 degrees Celsius on the packaging floor, or the cocoa butter could start to bloom. Even the workers' hands are often gloved, not just for hygiene, but to avoid leaving fingerprints on freshly wrapped bars. In large facilities, the scale borders on unbelievable. A single tempering machine can handle over 2 tons of chocolate per hour. Continuous production lines can run 24 hours a day, 7 days a week, turning raw cocoa beans into finished bars in less than 48 hours. Some factories produce more than 100,000 bars a day, enough to stretch for kilometers if laid end to end. Behind all that automation, there's still an underlying fragility. Chocolate doesn't forgive mistakes. A few degrees too warm, a few minutes too long in conching, or a small variation in cocoa butter content can ruin the entire batch's texture or shine. That's why every factory has a sensory lab nearby, where trained tasters break, smell, and taste samples under controlled conditions. They listen for that crisp snap, feel the melt rate on the tongue, and check the aftertaste for balance. Their judgment guides the machines, ensuring that industrial precision still serves flavor. The first ingredient, of course, is sugar, mountains of it. Pallets of fine white granules arrive in 50-kilogram sacks or bulk tankers that pour directly into stainless steel silos. Every grain is measured because in candy making, ratios decide everything: sweetness, hardness, and even shine. To that base, technicians add glucose syrup, which keeps the sugar from crystallizing, and sometimes invert sugar or corn syrup for extra smoothness. Water is added too, but not much. It's just enough to dissolve the sugar before the boiling begins. The heart of a candy factory is the cooker. It's not a simple pot on a stove, but a pressurized vacuum system designed to control heat down to the degree. Sugar syrup begins its journey at around 110 degrees Celsius and can climb well past 150 depending on the candy type. For hard candies, the syrup is cooked until nearly all the water evaporates, leaving a glossy liquid that hardens into glass as it cools. For softer sweets, like caramels or taffies, the process stops sooner, trapping more moisture inside. Inside these towering cookers, live steam circulates through jacketed walls, heating evenly, while automatic paddles keep the syrup moving to prevent scorching. Sensors constantly monitor temperature, pressure, and viscosity. A few seconds of overcooking can turn the entire batch bitter. When the syrup hits the precise target point, the system opens a valve and a golden stream pours into a cooling trough. Thick, shimmering, and bubbling like lava. The sound at this stage is mesmerizing. A slow, sticky crackle as the mixture meets cooler metal. If the candy is destined to be hard, it's spread into sheets and left to cool just enough to handle. The temperature window is narrow, too hot to touch, too cold to shape. Workers or mechanical arms fold and stretch it repeatedly on steel tables, introducing air for opacity and a lighter bite. Watching it twist and gleam under the lights, you realize candy isn't just food, it's a dance of heat and motion. Color and flavor come next. Small concentrated doses of fruit oils, acids, or natural extracts are poured onto the warm candy mass. Then the folding continues, spreading the flavor evenly through the glossy sugar. Food coloring, whether natural from beet and turmeric extracts or synthetic for vivid reds and blues, is kneaded in until the hue deepens and glows. In large factories, automated color injectors handle this job with perfect precision, ensuring that every batch of cherry or lemon candy matches exactly the one before. For striped or multicolored candies, the process gets even more theatrical. Separate batches are dyed different colors, then rolled and layered together like sugar clay. Machines pull and twist these layers into long patterned ropes. When you look at a peppermint swirl or a rainbow lollipop, that's the cross-section of one of those stretched ropes. Patterns engineered at the molecular level by temperature, timing, and geometry. Next comes shaping. The warm candy rope, still pliable and glowing, travels down conveyors toward forming machines. For lozenges and discs, high-speed rollers stamp them out at up to 1,000 pieces per minute. For lollipops, the rope is fed into molds, while sticks are inserted automatically, each one timed to within fractions of a second. The smell here is almost intoxicating. Sugar, fruit, and heat mixed with the faint metallic tang of machinery. As the candy cools, it hardens rapidly. Fans and chilled air help stabilize the shape. In some factories, candies pass through cooling tunnels, long chambers filled with dry, filtered air at around 20 degrees Celsius. It's crucial to keep moisture out. Even a hint of humidity can make the surface turn sticky. For softer varieties like taffy or caramels, humidity is controlled the other way, kept slightly higher to prevent cracking. Gummy candies take a completely different path. They start as a warm syrup made of sugar, glucose, water, gelatin, and fruit flavorings. The key ingredient, gelatin, acts as the scaffold, creating that chewy, elastic texture. Once mixed and filtered, the liquid gummy base is poured into molds made from starch powder. These molds, created by stamping impressions into trays of cornstarch, hold the candy's shape while absorbing excess moisture. Rows of trays move through filling machines that deposit the liquid mixture with the accuracy of a printing press. After filling, the trays enter drying rooms. For gummies, drying can take 1 to 2 days at controlled temperatures, allowing them to set and develop that perfect bounce. Once firm, the candies are gently tumbled out of the molds, brushed clean, and often coated with a fine layer of oil or wax to give them shine and prevent sticking. The starch is sifted, dried, and reused again and again, part of an endlessly repeating cycle. Meanwhile, another part of the factory might be making chewy caramels. Here, the syrup includes butter, milk, and sometimes cream, turning the process into a controlled caramelization. The fat content introduces extra complexity. The sugar browns more slowly, and the proteins in milk add nutty, toffee-like flavors. As the mixture cools, it's stretched and folded to trap tiny air bubbles that make each bite soft yet rich. The finished caramel sheets are cut by spinning blades, wrapped and sealed by twisting machines that can process hundreds per minute, each one a tiny pillow of golden chewiness. Then there's the world of coated candies, the kind with crisp sugar shells. The process begins with a batch of soft or chocolate centers, which are loaded into giant rotating drums called pans. As they tumble, fine sprays of sugar syrup coat the surface. Each rotation builds a paper-thin layer that dries before the next one is added. A single candy shell can have over 100 micro layers of sugar, each applied over hours. Once the coating is complete, colorants and polish are added, creating that unmistakable, glossy finish. The sound inside the panning room is hypnotic, a rhythmic swish of thousands of candies cascading over each other like pebbles in a stream. Hygiene and precision define every part of the factory. Floors slope toward drains for easy cleaning. The air is filtered to remove moisture and dust. Every pipe and valve is part of a clean-in-place system that can flush itself with hot water and sanitizer between batches. Workers wear full protective gear, not just for safety, but to prevent even a stray hair or droplet from disturbing the delicate sugar chemistry. In many plants, the relative humidity is maintained below 30% because sugar is hygroscopic. It pulls water from the air. A few minutes of exposure to humid air could ruin an entire day's production. Automation keeps the operation seamless. Sensors monitor the temperature of every batch in real time. If a syrup cooks too fast, the system instantly adjusts the steam pressure. Robots handle packaging, grabbing handfuls of candies, counting them precisely by weight, and dropping them into pouches or boxes. Labelers print barcodes and batch numbers automatically, allowing every piece of candy to be traced back to the exact tank of syrup it came from. Once sealed, the candies travel into large climate-controlled warehouses, often maintained around 18 to 20 degrees Celsius. There, pallets are stacked in symmetrical rows, waiting for distribution. Trucks with temperature control units arrive daily, bound for supermarkets and corner stores across the country. What began as simple sugar and water is now a rainbow of shapes and textures: chewy, crunchy, hard, soft, filled or coated. The scale is astonishing. A single production line can churn out over 10,000 lollipops an hour. Gummy lines can mold several million bears a day. Some facilities run continuously for weeks, stopping only for cleaning and recalibration. The output is measured not just in tons, but in smiles. Every piece looks effortless, but behind it lies an orchestra of steam lines, pumps, motors, and temperature probes working in perfect harmony.